Hello there, and welcome to Science for Sleep, the quiet corner of the internet where curiosity gets comfortable, complex ideas slow down a little, and science takes the scenic route toward rest. Tonight we're setting out on a journey through one of the strangest possibilities in modern physics, something that may have existed long before atoms, stars, or galaxies ever appeared. The topic is cosmic strings, mysterious objects that, if they exist, may be older than matter itself. But before we begin pulling on that thread, let me ask you something simple. Where in the world are you listening from tonight? Maybe it's late evening where you are, the day winding down and the lights in your home growing softer. Perhaps it's the quiet early hours of morning, when the world outside still feels half asleep. And just out of curiosity, what time is it right now in your little corner of the universe? It's an amusing question for a story like this, because the deeper we go into cosmology, the less straightforward time begins to feel. If you find this kind of gentle exploration soothing, or if the slow unfolding of the universe helps you relax at the end of the day, feel free to give the video a like and maybe subscribe to the channel. It helps this calm little community reach others who might also enjoy drifting through science at a quieter pace. Now then, let's settle in and start with a thought. Imagine the universe not as the vast collection of stars and galaxies we see today, but as something much younger, far hotter, and unimaginably dense. A place where matter, as we know it, didn't yet exist. No atoms, no planets, not even protons or neutrons. Just energy, space, and the rapidly changing rules of physics trying to settle into their modern forms. In that early era, the universe behaved very differently from the one we live in today. Temperatures were so extreme that the familiar building blocks of matter could not hold together. Forces that are now distinct, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may once have been unified into simpler interactions. The universe was not just smaller then, it was also stranger. And within that strange beginning, physicists believe something remarkable might have happened. As the universe cooled and expanded, it likely went through a series of transitions. Not transitions in the everyday sense like water freezing into ice, but similar in principle. When water cools, its molecules reorganize into a new structure. The same basic idea may apply to the universe itself. As temperatures dropped, the fundamental fields that shape reality may have shifted from one configuration to another. Whenever a system undergoes such a transition, imperfections can appear. You can see something similar in ordinary life. Think about a pond freezing on a cold night. The surface gradually turns into ice, but it rarely forms as one perfect sheet. Cracks appear. Lines spread across the surface where different regions freeze in slightly different orientations. These cracks are not separate objects placed on top of the ice. They are features formed during the transition itself. Now imagine a similar process, but happening not on a frozen pond, and not even within a single galaxy, but across the entire universe. In some theories of physics, the early universe may have developed structures that resemble extremely thin lines running through space. These lines would not be made of atoms or particles. Instead, they would be distortions in the fields that define the universe. They are sometimes described as topological defects, a term that sounds technical, but simply means a kind of imperfection in the arrangement of a field. One possible form of these defects is what scientists call a cosmic string. The name can be a little misleading at first. When we hear the word string, we tend to imagine something like thread or wire, something made of material that can bend or fray. Cosmic strings are not like that. They are not objects in the usual sense. They are more like extremely narrow regions where the fabric of space contains enormous energy. To picture this, it helps to start with an unusual comparison. Imagine stretching a sheet of rubber tightly across a frame. If you press down in one place with your finger, the sheet dips slightly. If you drag your finger across the surface, it leaves a narrow groove that moves along the rubber. Now suppose that groove were permanent, a narrow line where the rubber remained under tension. Cosmic strings are somewhat like that, except instead of rubber, The sheet is the structure of space itself, and the tension involved is beyond anything we encounter in everyday physics. These hypothetical strings could be incredibly thin. In fact, many models suggest they might be far narrower than an atomic nucleus. Yet despite their tiny width, they would carry enormous energy. A segment only a few kilometers long could contain as much mass energy as an entire mountain. That combination, extreme thinness and immense density, makes cosmic strings very different from familiar cosmic objects. A star, for instance, spreads its mass across a vast volume. Even a neutron star, one of the densest things we know, still has a diameter of around 20 kilometers. A cosmic string would concentrate huge amounts of energy into a line so narrow it would be almost impossible to see directly. If such objects formed during the early universe, they might still exist today, stretching across enormous distances. Some theoretical models suggest they could extend for millions or even billions of light years. Others predict that they might form loops of various sizes, slowly oscillating and releasing energy over time. The remarkable thing about these structures is that they would not be made of matter in the usual sense. They would be configurations of energy left behind as the universe settled into its current form. In other words, they might predate the formation of atoms entirely. That idea leads to an interesting perspective. When we look around today, the universe seems filled with matter. Stars burn hydrogen, planets form from dust and rock. Even the air around us is made of molecules assembled from atoms. It is easy to assume that matter is the primary ingredient of the cosmos, but in the earliest moments after the Big Bang, matter was not yet stable. The universe first consisted of fields and energy interacting at extremely high temperatures. Only later did particles form, and later still did atoms appear. If cosmic strings emerged during those earliest transitions, they might be among the oldest structures in existence, older than galaxies, older than stars, and perhaps even older than the particles that eventually built those stars. Of course, all of this raises a natural question. If cosmic strings could exist, why have we not clearly seen them? Part of the answer lies in how subtle their presence might be. Even though they would carry enormous energy, they would also be extremely thin. You would not expect them to glow or shine like a star. Instead, their main influence would come from gravity. Anything with mass or energy bends space around it. This idea comes from Einstein's theory of general relativity, which describes gravity not as a force pulling objects together, but as the curvature of space and time caused by mass and energy. A cosmic string, despite being incredibly narrow, would still contain immense energy. That means it would distort the geometry of space around it. However, the way it bends space is quite different from the gravitational field of a planet or star. Instead of pulling objects inward, a straight cosmic string would create a kind of wedge-shaped distortion in space. One way to visualize this is to imagine cutting a narrow slice out of a sheet of paper and then taping the edges back together. The surface remains mostly flat, but its geometry has changed slightly. Lines that used to run straight across the paper now take slightly different paths. In a similar way, space around a cosmic string could remain locally flat while still being globally distorted. Light passing near the string might follow unusual paths, creating distinctive patterns that astronomers could potentially observe. For instance, if a cosmic string lay between Earth and a distant galaxy, it might split the image of that galaxy into two identical copies sitting side by side in the sky. Unlike ordinary gravitational lensing, which usually stretches or magnifies images, this effect would produce nearly identical duplicates. Astronomers have searched for such signatures in telescope data, scanning the sky for pairs of galaxies that appear too similar to be coincidence. So far, no observation has provided clear confirmation. But the search continues. Another possible clue could come from gravitational waves. These are ripples in spacetime generated by massive objects in motion. In recent years, detectors such as LIGO have successfully observed gravitational waves produced by merging black holes and neutron stars. Cosmic string loops, if they exist, might also emit gravitational waves as they oscillate. Detecting such signals would not only confirm the existence of cosmic strings, it would also provide valuable information about the conditions of the early universe, offering a glimpse into physics at energies far beyond what we can achieve in particle accelerators. And that brings us back to the beginning of the story, the moment when the universe itself was still deciding what kind of place it was going to become. During those first fractions of a second, temperatures were so high that familiar physical laws were still taking shape. Fields shifted, symmetries broke, forces separated from one another as the cosmos expanded and cooled. In many theories, those transitions were not perfectly smooth. Just as freezing water forms cracks in ice, the early universe might have developed narrow defects where the fields did not align perfectly. Cosmic strings could be the result of those imperfections, long-lasting relics of a time when the entire universe was undergoing dramatic change. A moment ago, we were picturing the possibility that the universe might contain extremely ancient threads, structures formed so early that they could predate atoms, stars, and galaxies. To understand how such strange things might appear, it helps to slow down and look carefully at the first moments of cosmic history, the brief and astonishing period when the universe itself was just beginning. When people talk about the beginning of the universe, they often imagine a kind of explosion, something dramatic and fiery expanding outward into empty space. The phrase Big Bang certainly encourages that mental picture, but the reality, according to modern cosmology, is a little different. The Big Bang was not an explosion inside space, it was the expansion of space itself. There was no centre from which everything blasted outward. Instead, every region of the universe began extremely hot, extremely dense, and extremely close together. Then space expanded, stretching the distances between points everywhere at once. If that idea feels slightly odd, that is perfectly normal. Human intuition evolved to deal with things like falling apples, flowing rivers, and occasionally stubborn furniture. It did not evolve to handle the birth of the cosmos. Still, with a bit of patience, the picture begins to make sense. Today the universe is vast and relatively cool. Galaxies drift through space, stars burn quietly for billions of years, and the temperature of the cosmic background radiation sits only a few degrees above absolute zero. But if we rewind the cosmic clock, moving backward through time, the universe gradually becomes smaller, denser, and hotter. Stars disappear first as temperatures rise. Galaxies dissolve into clouds of gas and radiation. Eventually, even atoms cannot survive. Electrons and nuclei separate into a hot plasma where light scatters constantly and nothing can travel far without interacting with something else. Keep going further back, and things become even more extreme. Protons and neutrons themselves break apart into smaller components called quarks. The universe becomes a dense soup of fundamental particles moving at enormous energies. Temperatures reach trillions of degrees. At that stage, matter as we usually understand it is barely recognizable. Continue rewinding, and the physics becomes more uncertain. The conditions become so extreme that our current theories start to lose their reliability. Physicists can still make educated guesses about what might have happened, but the closer we get to the beginning, the more speculative the picture becomes. Even so, there are certain milestones in the early history of the universe that scientists can describe with reasonable confidence. These milestones occurred astonishingly quickly. To give you a sense of scale, imagine dividing 1 second into 1 billion pieces, then divide one of those pieces into another billion pieces. Now divide again. The earliest meaningful moments of cosmic history unfold on timescales even shorter than that. For example, one of the first periods physicists often discuss is called the Planck era. This lasted only about 10 to the minus 43 seconds after the beginning. That number is so small it almost refuses to behave like a normal unit of time. During the Planck era, the universe was so hot and dense that gravity, quantum mechanics, and the other fundamental forces were all tangled together in ways we still do not fully understand. Our current theories cannot describe this phase properly, because we do not yet have a complete theory of quantum gravity. So for now, the Planck era remains something of a mystery. Shortly after that, the universe entered a stage known as the Grand Unification era, at least according to many theoretical models. During this time, the strong nuclear force, the weak nuclear force, and electromagnetism may have been combined into a single unified interaction. In the everyday world, we experience these forces separately. Electromagnetism governs electricity and magnetism. The strong force binds atomic nuclei together. The weak force drives certain types of radioactive decay. But in the early universe, when energies were incredibly high, those forces may have been different expressions of the same underlying field. As the universe cooled slightly, that symmetry could have broken, separating the forces into distinct interactions. This moment when a unified force split into multiple forces is one of the key ideas in understanding how cosmic strings might form. But before we get there, something else very dramatic may have happened. Roughly around 10 to the minus 36 seconds after the beginning, the universe may have experienced a period called cosmic inflation. Inflation is one of the most remarkable proposals in modern cosmology. According to this idea, the universe briefly expanded at an almost absurd rate, far faster than the speed of light. Not because objects were moving through space that quickly, but because space itself was stretching extremely rapidly. During inflation, the size of the observable universe could have grown from something smaller than an atom to something roughly the size of a grapefruit in an incredibly tiny fraction of a second. If that sounds difficult to imagine, that is because it truly is. Even physicists sometimes resort to slightly humorous analogies when discussing inflation, partly because the numbers involved are so enormous. One way to think about it is this. Imagine drawing a small dot on a balloon. Now inflate the balloon rapidly. The dot stretches apart from every other point on the surface as the rubber expands. Inflation works in a somewhat similar way, except instead of a balloon, it involves the fabric of space itself. There are several reasons why scientists think inflation may have occurred. For one thing, it helps explain why the universe looks remarkably uniform in all directions. When astronomers measure the temperature of the cosmic microwave background radiation, they find that it is almost the same everywhere. Without inflation, it would be difficult to explain how distant regions of the universe managed to become so similar. Inflation also helps explain why the geometry of the universe appears very close to flat, rather than strongly curved. The rapid expansion would have smoothed out large-scale curvature, much like inflating a balloon makes a small patch of its surface appear flatter. When inflation ended, the universe continued expanding, but at a more moderate pace. The enormous energy that had driven inflation converted into a hot mixture of particles and radiation. At this stage, the cosmos was filled with a dense, energetic plasma where particles constantly collided, created new particles, and annihilated with their opposites. This era was chaotic, but also structured by the laws of physics that had now begun to settle into their modern forms. During the first tiny fractions of a second, several important transitions occurred. These transitions were somewhat like the phase changes we see in everyday materials, except they involved fundamental fields rather than water or metal. As the universe cooled, certain symmetries in those fields broke. Symmetry breaking is a curious concept that shows up throughout physics. A simple example comes from a pencil balanced perfectly on its tip. In theory, it could fall in any direction. The system is symmetrical because no direction is preferred. But the moment the pencil begins to tip, the symmetry breaks. It falls in one particular direction, and the symmetry is gone. In the early universe, something similar may have happened with the fundamental fields that define the forces of nature. At extremely high temperatures, the fields may have existed in symmetrical states where different configurations were equally possible. As the universe cooled, those symmetrical states became unstable, and the fields settled into specific arrangements. And here is where things start to get interesting. When a large system undergoes symmetry breaking, it does not always settle perfectly everywhere at once. Different regions can choose slightly different configurations. Where those regions meet, mismatches can occur. Those mismatches are called topological defects. You can see a familiar version of this effect in certain crystals. As molten material cools and solidifies, different regions of the crystal can form with slightly different orientations. Where the regions meet, defects appear. In the early universe, if fields settled into different configurations in different places, narrow defects might have formed along the boundaries between those regions. Depending on the details of the physics involved, those defects could take several forms. Some might appear as point-like structures, others could form sheet-like surfaces, and in some cases the defects could form long, narrow lines extending across space. Those line-like defects are what physicists refer to as cosmic strings. They would not be strings in the everyday sense, but rather stable regions where the field configuration remained trapped in a higher energy state than the surrounding space. Because the energy difference could be enormous, the resulting structures would carry immense tension, like extremely tight elastic bands embedded in spacetime. Another remarkable aspect is that once formed, these strings could be incredibly stable. In many models, they would not simply dissolve or decay quickly. Instead, they could persist as the universe expanded, stretching across vast distances. Some strings might form closed loops. Others might extend almost indefinitely. Over time, these strings could move, vibrate, and occasionally intersect with one another. When they crossed paths, they might reconnect and form new loops that oscillate and gradually release energy. All of these processes would happen quietly on cosmic scales, invisible to ordinary observation, but potentially detectable through their gravitational effects. The important thing to remember is that the seeds of these structures, if they exist, would have been planted extremely early in cosmic history, long before the first atom formed, long before the first star ignited, long before galaxies gathered into the graceful spirals and clusters we observe today. The universe, in those first moments, was a place of rapid transformation. Fields rearranged themselves, forces separated, energy condensed into particles, and in the midst of those changes subtle imperfections may have formed. Those imperfections might still be out there today, stretched across the vastness of space like nearly invisible threads woven into the structure of the cosmos. Earlier we spent some time drifting through the very first moments of cosmic history, a period when the universe was incredibly hot, incredibly dense, and changing extremely quickly. During those first fractions of a second, the rules that govern reality today were still settling into place. Forces were separating, particles were forming, and the entire cosmos was gradually cooling as space expanded. Now, something important happens whenever a system cools down and changes state. Whether it's water turning into ice, metal solidifying after being melted, or even a crowd of people gradually organizing themselves into lines, transitions rarely occur perfectly everywhere at once. Small differences appear from one region to another. The early universe was no exception. To understand why this matters, it helps to think about how physicists describe the fundamental structure of reality. In modern physics, the universe is not simply made of particles floating in empty space. Instead, it is filled with fields. These fields exist everywhere, and particles are often described as small excitations or disturbances within those fields. One of the simplest ways to picture a field is to imagine the temperature in a room. The temperature has a value at every point in the space around you. Some areas might be slightly warmer or cooler than others, but the field itself exists everywhere in the room. In physics, there are fields that correspond to the forces of nature and to the particles that carry those forces. The electromagnetic field, for example, is responsible for electricity, magnetism, and light. Other fields are associated with quarks, electrons, and neutrinos. In the earliest moments of the universe, many of these fields behaved differently from how they behave today. At extremely high temperatures, some of the distinctions between forces may not have existed yet. Instead of separate interactions like electromagnetism and the weak nuclear force, there may have been a more symmetrical arrangement where these forces were unified. Symmetry plays a surprisingly important role in physics. When physicists talk about symmetry, they usually mean that a system looks the same under certain transformations. For instance, a perfect sphere looks identical no matter how you rotate it. That rotational symmetry tells you something about the sphere's structure. The early universe may have possessed symmetries of a different kind, symmetries built into the underlying laws that govern fields and particles. These symmetries describe situations where different configurations of the fields are equally possible, but symmetries do not always last. As the universe expanded and cooled, some of these symmetrical arrangements became unstable. When that happens, the system must settle into one of several possible states, and this process is known as symmetry breaking. A familiar example of symmetry breaking comes from a simple object like a pencil balanced perfectly on its tip. In theory, the pencil could fall in any direction. All directions are equally possible, which means the system is symmetrical, but the moment the pencil begins to fall, it chooses one particular direction. The symmetry is broken, and the pencil ends up lying on the table in a specific orientation. Now imagine something similar happening across the entire universe. At very high temperatures, a field might sit in a symmetrical configuration where multiple states are equally valid. As the temperature drops, that symmetrical state becomes unstable, and the field must choose one of several possible configurations. The key detail is that different regions of the universe might choose differently. Remember that in the early universe, signals could not travel instantly from one place to another. Even though space was much smaller than it is today, the speed of light still limited how quickly information could spread. So when a symmetry broke, one region of space might settle into one configuration, while another region settled into a slightly different one. Where those regions met, the field would not match perfectly. And that mismatch is exactly where interesting structures could form. Physicists call these structures topological defects. The name sounds complicated, but the idea is actually quite straightforward. A topological defect is simply a stable irregularity in the arrangement of a field. To see an example in everyday life, imagine a large group of people trying to point in the same direction. Suppose they are standing in different rooms, and each group decides independently which way to face. Later, when the doors open and the groups meet, you might find places where the orientations do not line up perfectly. Where those mismatches occur, boundaries appear. In materials like crystals, these boundaries are called defects. In the early universe, similar boundaries could appear in the configuration of fundamental fields. Depending on the details of the symmetry breaking, these defects could take several different forms. Some might appear as point-like structures, others might form surfaces, and in certain cases they could appear as long, thin lines extending across space. Those line-like defects are what physicists call cosmic strings. But before we focus entirely on strings, it helps to explore the idea of phase transitions in a bit more detail. In everyday life, phase transitions happen all the time. Water freezes into ice, boils into steam, or condenses into liquid. These changes occur when temperature or pressure passes certain thresholds. During the freezing process, for example, water molecules gradually arrange themselves into a regular crystal pattern. However, this process does not occur perfectly everywhere at once. Small crystals form in different places, each with its own orientation. When these growing crystals meet, the patterns sometimes fail to line up exactly, leaving behind defects in the ice. If you have ever looked closely at frost forming on a window, you may have seen intricate patterns spreading outward from many starting points. Where those patterns meet, tiny lines or boundaries appear. The early universe may have undergone something similar, but instead of water molecules organizing into ice crystals, fundamental fields were reorganizing into lower energy configurations. each region of space may have settled into a particular state independently, and where those regions met, the fields could become trapped in configurations that could not easily be smoothed out. Once formed, these trapped configurations might remain stable for extremely long periods of time. Cosmic strings, if they formed in this way, would be an example of such a trapped structure. The reason they can persist lies in the mathematics of topology. Topology is a branch of mathematics that studies properties of shapes that remain unchanged when objects are stretched or deformed without tearing. A famous example often used in topology discussions is the relationship between a donut and a coffee mug. Both objects have one hole, and in topological terms, they can be smoothly transformed into one another. Topological defects arise when the structure of a field contains features that cannot be removed without a drastic rearrangement of the system. Imagine tying a knot in a rope. Once the knot is there, you cannot remove it simply by smoothing the rope. You would have to untie the knot or cut the rope entirely. Cosmic strings behave somewhat like knots in the configuration of a field. They represent regions where the field cannot relax into the lowest energy state, because the surrounding configuration prevents it. As a result, the energy remains concentrated along a narrow line. Another interesting feature of cosmic strings is the tension they would possess. In physics, tension refers to the tendency of an object to contract under stress. A stretched rubber band, for example, has tension because it wants to shorten. Cosmic strings would have extraordinary tension due to the enormous energy stored along their length. In many models, the tension of a cosmic string would be so large that even a tiny segment could exert gravitational effects strong enough to influence nearby matter and light. But despite their immense tension, cosmic strings would not necessarily behave like ordinary objects. For example, if you tried to grab a cosmic string, which is not recommended for several reasons, you would not find a solid thread. Instead, you would encounter an intense region of energy where the fields of the universe were arranged in an unusual configuration. Fortunately, the chances of encountering such an object locally are extremely small. If cosmic strings exist at all, they would most likely be spread across vast cosmic distances, far from our everyday surroundings. Still, their presence could subtly influence the large-scale structure of the universe. Some early cosmological models even suggested that cosmic strings might have helped seed the formation of galaxies. As strings moved through space, their gravitational effects could have drawn matter together, creating the initial density variations that later grew into galaxies and clusters. Later observations of the cosmic microwave background suggested that cosmic strings were not the dominant cause of galaxy formation. However, that does not mean they cannot exist. It simply means their role may be smaller than once imagined. Even today, researchers continue searching for signs of these structures. One reason the search continues is that cosmic strings could reveal information about extremely high-energy physics. The conditions under which they might form correspond to energies far beyond what we can recreate in particle accelerators. In other words, if we discovered cosmic strings, they could act as natural laboratories for studying physics from the earliest moments of the universe. That possibility keeps the idea very much alive in theoretical research. It is also worth remembering that the universe was not perfectly smooth even after these early transitions. Tiny fluctuations in density and temperature already existed. Those fluctuations eventually grew under the influence of gravity, forming the cosmic structures we see today. But alongside those fluctuations, the universe might also have contained something more dramatic. Long, narrow defects stretching across enormous distances, formed when the young cosmos settled into its present configuration. By this point in the story, we have followed the young universe through its earliest changes. We saw how extreme temperatures allowed forces to behave differently, and how the cooling cosmos may have passed through a series of transitions as its fundamental fields rearranged themselves. Those transitions were not necessarily smooth everywhere at once. Different regions could settle into slightly different configurations, and where those regions met, mismatches could appear. Those mismatches are the starting point for something quite fascinating. To understand what scientists mean when they describe cosmic strings as cracks in the fabric of reality, it helps to pause and look at a few everyday examples where similar patterns appear in ordinary materials. Imagine a wide lake in the middle of winter. As the temperature drops, the surface gradually begins to freeze. At first, small patches of ice form in different places. Each patch spreads outward as the freezing process continues. Eventually, the patches meet, and when they do, the boundaries between them often form long, thin lines. These lines are cracks or seams where the growing regions did not align perfectly. The important thing to notice is that those cracks are not separate objects placed onto the ice afterward. They are features created by the freezing process itself. The ice sheet formed, but the process left behind narrow lines that mark where the formation was imperfect. Now imagine something like that happening on the scale of the entire universe. During the earliest fractions of a second, the universe was filled with energetic fields rather than familiar objects like atoms or molecules. As the cosmos expanded and cooled, those fields began settling into stable configurations. In many theoretical models, the process was similar to a phase transition in materials. However, because the universe is enormous, even when it was very young, different regions could settle into their new states independently. Picture an enormous landscape where every point must decide which direction to face. If nearby points communicate with each other, they might coordinate their choice. But if the landscape is too large for signals to travel instantly, distant regions may choose differently. Where those choices meet, boundaries appear. Those boundaries are what physicists refer to as topological defects. The word topological refers to the mathematical properties of shapes and configurations that cannot be changed without tearing or cutting. In this context, it describes defects that cannot simply smooth themselves out because of how the field is arranged around them. To make that idea more concrete, consider a simple analogy involving arrows drawn on a sheet of paper. Imagine you fill a large sheet with arrows that all point in roughly the same direction. Now suppose that in different parts of the sheet, people independently choose which way their arrows should face. When the groups meet, there may be places where the arrows cannot all smoothly align. Somewhere in the sheet, a boundary forms where the directions shift abruptly. In a material system, that boundary might slowly disappear as the atoms rearrange themselves. But in certain field configurations, the boundary becomes locked in place, because removing it would require the entire field to reorganize dramatically. When that happens, the defect can remain stable. In the early universe, the fields that governed fundamental forces may have experienced exactly this kind of process. When the symmetry of a field breaks during a phase transition, the field must choose a particular configuration. If neighbouring regions make different choices, the mismatch can produce defects. Depending on the nature of the field and the symmetry involved, those defects can take several forms. One possibility is a point defect. This would resemble a small region where the field cannot settle properly at a single location. Another possibility is a sheet-like defect, a two-dimensional surface separating regions with different configurations. But there is also a third possibility that turns out to be especially intriguing. In some cases, the defect takes the form of a long, narrow line running through space. This line is what physicists call a cosmic string. Calling it a string can make the concept sound familiar, but the resemblance to everyday thread is limited. A cosmic string is not a piece of material stretched through space. Instead, it is a narrow region where the underlying field remains trapped in a higher energy state. The surrounding space has settled into its stable configuration, but along the string the field cannot complete that transition. As a result, energy remains concentrated along a thin line. Another way to think about it is to imagine twisting a rubber band into a loop and then tying a knot in it. Once the knot forms, it cannot simply vanish by itself. You would need to untie the knot or cut the band. Cosmic strings behave somewhat like knots embedded in the structure of fields. They represent regions where the configuration cannot be smoothed out without drastic changes in the surrounding space. Because of that, they can remain stable for extremely long periods of time, potentially even billions of years. An interesting aspect of these structures is how thin they might be. Many theoretical models suggest that the width of a cosmic string could be extraordinarily small, far smaller than an atomic nucleus. Despite this microscopic width, the energy stored along the string would be enormous. To illustrate the scale involved, imagine compressing the mass of a large mountain into a line thinner than a single proton. That comparison still underestimates the density that some models predict. The reason the energy becomes so concentrated is that the field along the string remains stuck in a high-energy configuration. The surrounding space has relaxed into a lower energy state, but the defect prevents the field inside the string from doing the same. This energy difference creates enormous tension along the string. In fact, cosmic strings would behave somewhat like extremely tight elastic bands embedded in spacetime. Their tension would constantly try to shorten them, pulling them into straighter shapes. If a cosmic string formed a closed loop, the tension would cause the loop to shrink. As it shrank, it might oscillate or wiggle, releasing energy in the form of gravitational waves. These oscillating loops are one of the ways physicists hope cosmic strings might eventually be detected. But before we talk more about detection, it is worth considering another property that makes cosmic strings unusual. Unlike ordinary objects, they would not exert gravity in quite the same way. When we think about gravity, we often picture objects pulling on each other. A planet attracts nearby objects. A star pulls gas inward. A black hole draws matter toward its center. Cosmic strings behave differently because their energy is concentrated along a line rather than spread through a volume. Instead of pulling objects directly toward them, they would change the geometry of space around them. A helpful way to picture this is to imagine removing a thin wedge from a sheet of paper and then taping the edges together again. The surface still looks flat in a small region, but the overall geometry has changed. Lines that once travelled straight across the sheet now take slightly different paths. Space around a cosmic string would behave in a similar way. Rather than forming a deep gravitational well like a planet or star, the string would create a wedge-like distortion. Light travelling near the string would follow curved paths, because the geometry of space had been altered. One potential observational effect of this distortion involves the bending of light from distant galaxies. If a cosmic string passed between Earth and a faraway galaxy, it could produce two identical images of that galaxy separated by a small angle. Unlike ordinary gravitational lensing, which often stretches or magnifies images, this effect would create nearly identical duplicates. Astronomers have searched for such duplicated galaxy images as possible evidence of cosmic strings. So far, none of the candidates has provided convincing proof, but the search continues as telescopes become more powerful and surveys of the sky grow more detailed. Another interesting property of cosmic strings is that they could move through space. Because they possess tension, they would behave somewhat like flexible lines under enormous stress. Segments of string might wiggle or oscillate as they evolved. When two segments of string intersect, something unusual could happen. Instead of simply passing through each other, the strings might reconnect. In this process, the segments exchange partners, creating new loops or altering their paths. This behavior is known as intercommutation. The newly formed loops would then begin to shrink under tension, radiating energy as gravitational waves while they oscillate. Over long periods of time, these processes could gradually reduce the number of strings in the universe, leaving behind fewer but still potentially enormous structures. The possibility that such defects formed during the early universe has fascinated physicists for decades. Cosmic strings offer a window into extremely high-energy physics, far beyond the reach of current particle accelerators. If they exist, they would carry information about the conditions present during the first fractions of a second after the Big Bang. In other words, they could act like fossils from the earlier stage of cosmic history. And yet, despite all this theoretical interest, cosmic strings remain hypothetical. The evidence for them has not yet appeared clearly in observations. But the idea persists because it emerges naturally in many theoretical models describing the early universe. Whenever a symmetry breaks in a certain way, the mathematics often predicts that line-like defects could form. Whether those defects actually formed in our universe remains an open question. Still, imagining the possibility leads to a remarkable picture. The universe we see today appears smooth and spacious, filled with galaxies drifting slowly apart. But hidden within that vastness there might be narrow seams where the early cosmos did not align perfectly. Long lines of concentrated energy, stretching across unimaginable distances, formed when the universe cooled and changed state. Not objects made of matter, but traces of ancient transitions preserved in the structure of space itself. And if those traces exist, understanding what they are, how they behave, and how they might be detected means looking more closely at the objects themselves. Because once we accept the possibility that such cracks could form, the next question becomes surprisingly simple. What exactly would a cosmic string be? Take a moment to picture the thinnest object you can easily imagine, perhaps a strand of spider silk glistening in the morning light, or a single filament from a piece of fabric pulled loose from a sleeve. Those things are incredibly small compared with most objects we encounter in daily life. Yet even something as delicate as spider silk is still unimaginably thick, compared with what physicists mean when they talk about a cosmic string. The phrase cosmic string sounds simple, almost familiar, but the object it describes is anything but ordinary. A cosmic string is not made from atoms, molecules, or any conventional form of matter. It is not something you could hold, cut, or tie into a knot with your hands. Instead, the term refers to a narrow region in space, where enormous energy has become trapped in a particular configuration of a field. That may sound abstract at first, so it helps to approach the idea slowly. In modern physics, the universe is described as a collection of fields that fill all of space. Some of those fields are associated with forces, such as the electromagnetic field that produces light and electricity. Others correspond to particles like electrons and quarks. Even what we call empty space is actually filled with these fields, quietly existing everywhere whether we notice them or not. Particles themselves are often described as small disturbances or excitations in those fields. If you imagine the surface of a calm pond, a ripple moving across the water could represent a particle travelling through space. The pond itself represents the underlying field. Most of the time, the fields in the universe sit in what physicists call a low-energy state. In simple terms, that means the fields have settled into stable configurations. But under certain conditions, especially during the early stages of cosmic history, those fields may have been forced into different arrangements. When the universe cooled after the Big Bang, some of the fields went through transitions. During those transitions, regions of space could settle into slightly different states. Where those regions met, the field sometimes could not smoothly align everywhere. The result could be a narrow boundary where energy remained trapped. If that boundary formed a long line extending through space, physicists would call it a cosmic string. The key idea is that the string is not a piece of matter stretched through the universe. Instead, it is a kind of defect in the structure of a field. The surrounding space has relaxed into its lowest energy configuration, but along the string, the field remains stuck in a higher energy arrangement. That trapped energy is what gives the string its remarkable properties. One of the first things physicists noticed when studying these objects was just how dense they would be. The width of a cosmic string might be incredibly small, far smaller than an atomic nucleus. In some models, the width is comparable to the scale associated with extremely high energy physics, something around a trillionth of a meter. Despite that microscopic thickness, the energy stored along the string could be immense. To get a rough sense of the scale, imagine compressing the mass of an entire mountain into a line no thicker than a proton. Even that comparison may underestimate the energy involved in some theoretical models. Physicists often describe the energy per unit length of a cosmic string using a parameter called tension. In everyday objects, tension refers to the force that tries to shorten something under stress. A stretched rubber band has tension because it pulls inward, trying to contract. Cosmic strings would have an extraordinary amount of tension. The energy along their length would constantly try to pull the string tighter and straighter. Because of this enormous tension, cosmic strings would behave in ways that differ from most objects in the universe. If a cosmic string formed a loop, for example, the tension would cause the loop to shrink. As it shrank, it could oscillate, much like a vibrating rubber band, although the energy involved would be vastly greater. Those oscillations could produce gravitational waves, ripples in space-time that travel across the universe. Another striking feature of cosmic strings is how they interact with gravity. In general relativity, gravity arises because mass and energy curve space-time. Planets, stars, and galaxies bend the space around them, causing objects and light to follow curved paths. A cosmic string also contains mass energy, but the geometry it creates is somewhat unusual. Instead of forming a deep gravitational well like a star or planet, a straight cosmic string changes the overall shape of space around it. One common way to describe this effect involves imagining a flat sheet of paper. Suppose you cut out a thin wedge from the sheet and then tape the edges back together. The surface remains mostly flat, but the geometry is subtly altered. Lines drawn across the sheet will behave differently because part of the original area has been removed. Space around a cosmic string behaves in a somewhat similar way. Rather than pulling objects toward it in the usual sense, the string effectively removes a tiny slice from the surrounding geometry of space. Light travelling on either side of the string can appear to take different paths, even though locally the space remains flat. This unusual geometry leads to one of the most interesting observational effects associated with cosmic strings. If a cosmic string passed between Earth and a distant galaxy, the light from that galaxy could be split into two identical images. Both images would appear side by side in the sky because the string altered the paths the light could take. Astronomers have looked for such duplicated galaxy images in large sky surveys. Although some candidates have appeared over the years, none has yet provided convincing evidence that cosmic strings are present. Still, the search continues. Another property worth mentioning is that cosmic strings could be extremely long. Some might stretch across distances comparable to the size of galaxies, or even larger regions of the universe. Others might form closed loops. These loops would move and oscillate as the universe evolves. When segments of string intersect, they could reconnect, creating new loops that gradually lose energy through gravitational radiation. Over long periods of time, the network of strings could change as loops form and disappear. Although cosmic strings are hypothetical, the mathematics describing them appears naturally in many theoretical models. In particular, they arise in certain versions of grand unified theories, which attempt to describe how the fundamental forces of nature might merge at extremely high energies. In those theories, the early universe contained fields with symmetrical properties. As the universe cooled, those symmetries broke, forcing the fields to settle into lower energy states. If different regions of space chose slightly different states during that process, line-like defects could form along the boundaries. Those defects would be cosmic strings. An interesting detail is that once such a defect forms, it cannot easily disappear. The surrounding field configuration prevents the defect from simply smoothing itself out. Removing the string would require the entire field arrangement to change in a complicated way. Because of this, cosmic strings could remain stable for extremely long periods of time. In fact, if they formed shortly after the Big Bang, some of them might still exist today. The universe has expanded enormously since those early moments, but the strings would expand with it, stretching across space as the cosmos grew larger. This possibility has fascinated cosmologists for decades. If cosmic strings exist, they would represent physical relics from extremely early cosmic history. Studying them could reveal information about energy scales far beyond what we can currently achieve in particle accelerators. For comparison, the most powerful particle accelerator on Earth, the Large Hadron Collider, reaches energies of around 10 trillion electron volts. The processes that might produce cosmic strings could involve energies billions of times greater. Detecting a cosmic string would therefore provide clues about physics operating at those extraordinary scales. Of course, the challenge is that cosmic strings would be extremely difficult to observe directly. They would not emit light like stars. They would not form glowing clouds like nebulae. Instead, their presence would mainly be revealed through subtle gravitational effects. Those effects might include unusual gravitational lensing, bursts of gravitational waves, or small distortions in the cosmic microwave background radiation. Researchers continue to look for these signals using increasingly sensitive instruments. Despite the difficulty of detection, the concept of cosmic strings remains appealing because it connects several important ideas in physics. It links cosmology, particle physics, and field theory into a single framework that attempts to explain how the early universe evolved. At the same time, it challenges our intuition about what an object can be. A cosmic string is not made of atoms, yet it carries enormous energy. It is thinner than anything we can easily imagine, yet it may stretch across cosmic distances. It behaves partly like a line under tension, and partly like a distortion in spacetime itself. Understanding these objects requires thinking about the universe not just as a collection of things, but as a dynamic network of fields capable of forming structures in unexpected ways. And once we accept that such structures might exist, another intriguing idea emerges. If cosmic strings truly formed during the earliest transitions of the universe, then their origins may go back to a time before the familiar particles of matter had even appeared. In other words, these strange lines of trapped energy might have existed before protons, before electrons, before atoms had a chance to assemble. How could something exist before the matter that makes up the visible universe today? Long before the first atom assembled itself, the universe already contained the ingredients that would eventually make matter possible. This may sound strange at first, because when we look around today, the cosmos appears to be built almost entirely from matter. Planets are made of it, stars burn it, and even the air in a quiet room consists of molecules drifting through space. Yet in the earliest moments after the universe began expanding, matter in the familiar sense did not exist at all. Instead, the young universe was dominated by energy and fields. At extremely high temperatures, the distinction between particles and energy becomes less clear than it appears in everyday life. In physics, matter and energy are closely related through Einstein's famous relationship equals mc square. That equation tells us that mass is simply a concentrated form of energy. Under the right conditions, energy can convert into particles, and particles can convert back into energy. During the earliest fractions of a second after the Big Bang, temperatures were so high that particles could not remain stable for long. Collisions constantly created new particles and destroyed others. The universe behaved more like an energetic sea of interacting fields than a collection of solid objects. Because of this, the concept of matter, in the ordinary sense, only became meaningful later, once the universe cooled enough for particles to survive for longer periods. This detail is important when discussing cosmic strings. If cosmic strings formed during the earliest phase transitions of the universe, then their origin might lie in a period before stable particles had appeared. In that sense, they would truly be older than matter. Understanding why requires a closer look at what physicists mean by fields. In modern theories of particle physics, every type of particle is associated with a field that fills all of space. The electron, for instance, is linked to the electron field. Quarks correspond to quark fields. Photons arise from the electromagnetic field. These fields are not confined to particular locations. They exist everywhere, even in regions that appear completely empty. Particles appear when these fields become excited in specific ways. A useful comparison is the surface of water. The water exists across the entire pond, but a ripple moving across the surface represents a localized disturbance. In this analogy, the pond represents the field and the ripple represents a particle. The early universe contained many such fields interacting at extremely high energies. When the universe cooled, those fields gradually settled into stable configurations. However, during that process, certain transitions may have occurred, and those transitions could leave behind defects. To understand how that works, it helps to consider a simple example involving symmetry. Imagine placing a marble at the top of a perfectly round hill. From that position, the marble could roll down in any direction. All directions are equally possible, which means the situation is symmetrical. But once the marble begins to roll, the symmetry breaks. The marble chooses one particular direction and settles into a lower position on the hillside. In many physical systems, the lowest energy state is not symmetrical, even though the underlying rules are. The same concept applies to fields in particle physics. At extremely high temperatures, a field might exist in a symmetrical state where many configurations are equally likely. As the universe cools, that symmetrical state may become unstable, forcing the field to settle into one of several possible lower energy states. The choice of state may differ slightly from one region of space to another. Because the universe is large and signals travel at a finite speed, distant regions cannot coordinate their choices perfectly. When these regions meet, the field configuration may fail to align smoothly. The result can be a trapped defect. If that defect forms along a narrow line, the energy associated with the higher energy configuration remains concentrated there. That line becomes what physicists call a cosmic string. What makes this particularly interesting is that the formation of such defects does not require matter to exist first. The process involves the behavior of fields themselves. Fields existed throughout the early universe even before stable particles appeared. When the universe cooled and certain symmetries broke, the fields reorganized into new patterns. Cosmic strings would simply be locations where the field configuration could not complete the transition smoothly. This means the strings could have formed at extremely early times, perhaps during the first tiny fractions of a second after cosmic expansion began. To appreciate how early that might be, consider the timeline of particle formation. Within the first microsecond after the Big Bang, the universe was filled with a dense mixture of quarks and gluons. These particles had not yet combined into protons and neutrons. Only after the universe cooled further did quarks bind together to form the protons and neutrons that make up atomic nuclei. Several minutes later, those nuclei began combining in a process known as primordial nucleosynthesis, producing the first light elements such as hydrogen and helium. Hundreds of thousands of years later, electrons finally combined with those nuclei to form neutral atoms. That event allowed light to travel freely through space, producing the cosmic microwave background radiation we observe today. Compared with those milestones, the formation of cosmic strings would have occurred astonishingly early. If they arose during symmetry-breaking transitions associated with grand unified theories, they might have appeared when the universe was less than a billionth of a second old. In other words, cosmic strings could be among the oldest structures in existence. This idea carries an interesting implication. When we look at distant galaxies, we are seeing matter that formed long after those earliest transitions. Stars formed hundreds of millions of years after the Big Bang. Planets appeared later still. Life on Earth emerged billions of years after the first stars ignited. Cosmic strings, if they exist, would predate all of those things. They would be relics from a time when the universe had not yet produced atoms or molecules. Their existence would reflect the behavior of fields at energy levels far beyond anything we can currently reproduce in laboratories. Because of that, cosmic strings would provide valuable clues about fundamental physics. Particle accelerators such as the Large Hadron Collider allow scientists to study interactions at very high energies. Yet even the most powerful accelerators can only reach a tiny fraction of the energies present during the earliest moments of the universe. Cosmic strings, on the other hand, could preserve information about those extreme conditions. Their tension, structure, and behavior would depend on the specific properties of the fields that formed them. By studying their effects on space and matter, physicists could learn about processes that occurred at unimaginable temperatures and densities. Another intriguing aspect is how these strings would evolve over time. Because they carry enormous tension, cosmic strings would not remain completely static. They would move through space, oscillate, and occasionally intersect with one another. When two segments of string cross, they may reconnect, creating loops that break away from the larger structure. Those loops would shrink gradually as they radiate energy in the form of gravitational waves. Over billions of years, a network of cosmic strings could slowly evolve through these processes. Some loops might vanish entirely, while long segments might remain stretched across enormous distances. Despite this evolution, the original strings could still trace their origin back to those earliest cosmic transitions. In that sense, they would represent ancient features embedded in the structure of space-time itself. Their age would not be measured in millions or even billions of years alone, but in their connection to the moment when the universe first began settling into its present form. For cosmologists, that possibility is both exciting and challenging. Exciting because it suggests that the universe might contain direct remnants of its earliest physical processes. Challenging because detecting such remnants requires extremely careful observations. Cosmic strings would not glow or shine. They would reveal themselves only through subtle distortions of space-time, the bending of light, or the emission of gravitational waves. Nevertheless, the search continues, because confirming their existence would open a window into physics far beyond the reach of current experiments. And once we accept the possibility that these ancient structures could exist, another question naturally follows. If cosmic strings formed so early in cosmic history and stretched across immense distances, what might the universe actually look like if such threads were woven throughout its vast structure? Step outside on a clear night and look up for a moment. What you see appears scattered and spacious. Stars shine at different distances, galaxies drift quietly through immense volumes of space, and between them lies what seems like an enormous emptiness. At first glance, the universe does not resemble something woven or connected. It looks more like a vast open landscape filled with isolated islands of matter. Yet modern cosmology tells a slightly different story. When astronomers map the large-scale distribution of galaxies, the universe reveals a structure that is surprisingly organized. Galaxies are not spread randomly in all directions. Instead, they form long filaments, clusters, and walls separated by enormous regions with relatively few galaxies. This pattern is often called the cosmic web. The cosmic web was shaped mainly by gravity acting over billions of years, gradually pulling matter into filaments and clusters. But long before galaxies began forming, the early universe may have contained another kind of structure entirely, something much older and far more subtle. That possibility leads to an intriguing idea. The universe might contain thin lines of concentrated energy stretching across enormous distances, remnants from the earliest phase transitions in cosmic history. If those structures exist, they would resemble invisible threads woven through the fabric of space. Physicists call those threads cosmic strings. When the phrase "stitched together" is used in this context, it does not mean that cosmic strings physically tie galaxies together like rope connecting objects. Instead, the comparison comes from how these strings could form networks, stretching across vast regions of the universe. Imagine a large piece of cloth. At first glance it looks smooth and continuous, but if you examine it closely, you see that the cloth is made from countless threads interwoven into a pattern. Each thread runs through the fabric, sometimes straight, sometimes looping, occasionally crossing other threads along the way. Now imagine something similar happening on cosmic scales. During the early universe, symmetry-breaking transitions could have created line-like defects in the underlying fields of space. These defects would not be isolated in just one place. They could appear in many regions simultaneously, forming a network of strings spread across the expanding universe. Some of those strings might stretch across enormous distances, possibly even across regions larger than entire galaxies. Others might form closed loops. Over time, these strings would move, interact, and occasionally reconnect with one another. The network would gradually evolve as loops broke off, oscillated, and lost energy. In this sense, the universe could contain something like a loose mesh of ancient threads. The comparison to stitching becomes helpful because each cosmic string represents a line where the field configuration could not settle perfectly during the early phase transitions. The rest of space relaxed into its lowest energy state, but along those narrow lines the fields remained trapped in a different arrangement. Those lines would carry enormous energy and tension, making them stable features that could persist as the universe expanded. Another interesting aspect of this idea involves how large the strings might be. Cosmic strings would be incredibly thin, possibly far smaller than any particle we can directly observe, but their length could be astonishing. Some theoretical models suggest that strings might extend across billions of light years. To put that into perspective, the Milky Way galaxy is about 100,000 light years across. A cosmic string could be thousands or even millions of times longer than that. Because of this immense length, the strings would not behave like small objects drifting through space. Instead, they would stretch across entire regions of the cosmos, sometimes forming long arcs or straight segments. The network would not remain perfectly static. Tension along the strings would cause them to move and adjust their shapes over time. If two segments of string crossed paths, they might reconnect in a process known as intercommutation. When that happens, the strings exchange segments, creating new loops or altering their paths. Those loops would then oscillate, gradually shrinking as they release energy through gravitational radiation. This process could slowly reduce the number of strings over time, though some long segments might remain for billions of years. Another reason the idea of a cosmic network is interesting comes from how these strings interact with spacetime. Unlike ordinary objects, cosmic strings would not simply sit in space. Their enormous energy would affect the geometry of the surrounding region. Instead of producing a gravitational field like that of a star or planet, a cosmic string changes the structure of space in a different way. The presence of the string effectively removes a tiny wedge from the surrounding geometry. A helpful way to visualize this is to imagine a sheet of paper. If you cut out a thin triangular slice from the sheet and then tape the remaining edges together, the surface still looks mostly flat. But the geometry has changed slightly. Straight lines drawn across the paper will behave differently because a small portion of space has been removed. Light travelling near a cosmic string would experience a similar effect. Instead of bending gradually toward the string as it would near a massive object, the light would travel along straight paths through a space whose geometry had been subtly altered. As a result, distant objects might appear duplicated in the sky. If a cosmic string lay between Earth and a distant galaxy, light from that galaxy could reach us along two slightly different paths. Both paths would arrive from slightly different directions, producing two nearly identical images. This type of gravitational lensing would look different from the lensing produced by galaxies or clusters. Instead of stretching or magnifying the image, the string would create two copies separated by a narrow gap. Astronomers have searched for this effect in large sky surveys, looking for pairs of galaxies that appear unusually similar. Although several candidates have been examined, none has yet provided clear confirmation that cosmic strings are present. Still, the possibility remains. Another way cosmic strings might influence the universe involves the large-scale distribution of matter. In the past, some cosmologists proposed that strings might have helped seed the formation of galaxies. As strings move through space, their gravitational effects could have pulled matter toward them, creating dense regions that eventually formed galaxies. Later observations of the cosmic microwave background suggested that this process could not have been the main cause of galaxy formation. However, cosmic strings could still contribute smaller effects that are harder to detect. Even if they played only a minor role in shaping galaxies, their existence would still reveal important information about the earliest phases of the universe. This is why cosmologists remain interested in them. Cosmic strings provide a connection between cosmology and particle physics. Their properties depend on how fundamental fields behaved at extremely high energies, possibly associated with grand unified theories. If those theories are correct, the early universe passed through several transitions as it cooled. Each transition could have produced different types of topological defects. Among those defects, line-like structures would appear as cosmic strings. One remarkable consequence of this idea is that the universe could contain structures that formed almost instantly after the beginning of cosmic expansion, yet remain present billions of years later. They would not be made of atoms, stars, or galaxies. Instead, they would be remnants of the universe's earliest transformations, preserved in the arrangement of its fields. From our perspective today, those strings would be incredibly difficult to see. Their width would be far too small for any telescope to resolve directly. The only clues to their presence would come from indirect effects, such as gravitational lensing or bursts of gravitational waves. Yet even if they are invisible in ordinary light, their existence would mean that the universe is not entirely smooth beneath the surface. Hidden within the vast distances between galaxies, there could be long, narrow seams where the early cosmos did not align perfectly. Those seams would stretch across space like threads woven into an enormous cosmic fabric. And once that image takes shape, another interesting question arises. If these threads truly exist, carrying immense tension and energy despite their tiny width, what would it mean for a single strand to possess such extraordinary weight? Consider for a moment the weight of things we encounter in everyday life. A book resting on a table has weight. A car parked on a street has far more. A mountain contains an almost unimaginable amount of mass compared with anything we can lift or move ourselves. Yet even something as massive as a mountain spreads that weight across an enormous volume of rock. Its mass is distributed over many cubic kilometers of material. Now imagine compressing a large mountain into a line so thin that it is far smaller than an atom. That comparison begins to hint at the strange scale involved when physicists talk about the weight of a cosmic string. The word weight here needs a bit of clarification. In ordinary language, weight usually refers to the force that gravity exerts on an object near the surface of a planet. In physics, however, it is often more useful to talk about mass or energy. According to Einstein's famous equation E equals mc squared, mass and energy are interchangeable. Energy contributes to gravity in the same way that mass does. Because cosmic strings are regions where enormous energy is trapped within a field configuration, they behave gravitationally as if they contain an extraordinary amount of mass. Physicists often describe this property using the phrase energy per unit length. Instead of saying a cosmic string has a total mass like a planet or star, they measure how much energy is stored along each meter of the string. That value turns out to be astonishing. In many theoretical models, a cosmic string could contain so much energy that a segment only 1 kilometer long might weigh as much as a large mountain. Other models predict even greater densities, depending on the energy scale associated with the phase transition that created the string. At first, this may sound impossible. How could something so thin contain so much energy? The answer lies in how the string forms. As discussed earlier, cosmic strings are not made of atoms. They are defects in the configuration of a field that fills space. The field inside the string remains trapped in a higher energy state compared with the surrounding space. Because the region is extremely narrow, the energy becomes concentrated along a line. A useful analogy involves stretching a rubber band. When you stretch a rubber band, you store energy in it. The more you stretch it, the more energy it contains. If you release one end, the band snaps back, because the stored energy pulls it inward. Now imagine a rubber band that has been stretched enormously, far beyond anything possible in everyday materials. The tension would be immense. Cosmic strings behave somewhat like that, except the tension comes from the energy trapped in the field along the string. The surrounding space is settled into a lower energy configuration, while the interior of the string remains in a higher energy state. The difference between those states produces the tension. In many models, the tension of a cosmic string is equal to its energy per unit length. That means the string constantly tries to shorten itself, pulling straight under its own stress. This tension is one of the defining characteristics of cosmic strings. If a long cosmic string existed in space, it would naturally try to become as straight as possible. Any bends or loops would experience forces pulling them tighter. When loops form, they do not remain static. The tension causes them to oscillate and shrink. As they oscillate, they release energy, often in the form of gravitational waves. Those gravitational waves could travel across the universe, carrying information about the motion of the string. Another interesting consequence of the enormous energy stored in a cosmic string involves gravity. Normally, when we think about gravitational effects, we picture objects pulling other objects toward them. A planet pulls a satellite into orbit. A star pulls gas inward, eventually forming new stars. A black hole bends the paths of nearby matter and light. Cosmic strings behave differently. Although they contain enormous energy, their gravitational influence does not resemble the familiar pull of a massive body. Instead, they change the geometry of space around them. The reason for this unusual behavior comes from the way their mass is distributed. A planet or star spreads its mass across a volume. The gravitational field surrounding it gradually decreases with distance. Cosmic strings, however, concentrate their energy along an extremely thin line. Because of that, the space around a string does not curve into a deep well. Instead, it forms what physicists call a conical geometry. To picture this, imagine again the sheet of paper example. If you remove a thin wedge from the sheet and join the edges, the paper remains mostly flat. However, the overall geometry has changed slightly. Lines that once ran straight across the sheet now follow paths that reflect the missing wedge. Space around a cosmic string behaves in a similar way. The string effectively removes a small angle from the surrounding space. This does not create a strong gravitational pull in the usual sense, but it changes how objects and light move through the region. One of the most striking effects involves light travelling near the string. Because the geometry of space is altered, light from a distant galaxy could pass on either side of the string and reach an observer along two separate paths. The result would be two nearly identical images of the same galaxy appearing in the sky. Unlike the distorted arcs produced by ordinary gravitational lenses, these images would look remarkably similar because the string does not stretch or magnify the light. It simply changes the paths available for it to travel. Astronomers have searched for this kind of lensing effect as a possible sign of cosmic strings. So far, none of the candidates observed in the sky has been confirmed as a genuine cosmic string event. But the search remains ongoing because the effect would be distinctive if detected clearly. The enormous energy stored in a cosmic string also raises another question. If a string carried so much energy along its length, what would happen if one passed near Earth? Fortunately, the chances of encountering such an object locally are extremely small. If cosmic strings exist, they are likely spread across vast cosmic distances, far away from our planetary neighbourhood. Still, physicists have considered the possibility as a thought experiment. Because the string would be incredibly thin, it might pass through matter without interacting strongly with individual atoms. However, the gravitational distortion associated with it could produce noticeable effects. For example, if a cosmic string moved between two nearby objects, the altered geometry of space could shift their positions relative to one another. In theory, if a string passed between two observers looking at the same distant star, they might briefly see two identical images of that star before the effect disappeared. More dramatic scenarios have also been explored in theoretical studies. If a cosmic string loop were to oscillate rapidly, it might produce bursts of gravitational waves strong enough to be detected by sensitive instruments. Observatories such as LIGO and other gravitational wave detectors are capable of measuring extremely small distortions in space-time. Some scientists hope that future observations might reveal signals consistent with cosmic string loops. Another reason cosmic strings remain interesting is that their energy density depends on the energy scale of the phase transition that created them. If the strings formed during a grand unified phase transition in the early universe, their energy per unit length would be extremely large. If they formed during a later transition associated with lower energies, their density would be smaller but still substantial. Different theoretical models predict different values, which means detecting cosmic strings could help test those theories. In this way, cosmic strings would act like physical traces left behind by the earliest processes in the universe. Their enormous tension and energy would not come from matter in the usual sense, but from the arrangement of fields that existed long before atoms and molecules appeared. And that is what makes them so intriguing. A cosmic string would be almost unimaginably thin yet carry immense weight. It would stretch across cosmic distances while remaining narrower than any particle we can directly observe. Gravity is usually imagined as a pull. A planet pulls on a falling apple. The moon pulls on Earth's oceans, raising the tides. The sun holds the planets in their long, steady orbits. These images are so familiar that it is easy to assume gravity always behaves like an invisible force tugging objects toward massive bodies. However, the deeper explanation offered by Einstein's theory of general relativity describes gravity in a very different way. According to this view, massive objects do not simply pull on other objects through space. Instead, they change the geometry of space and time around them. Matter and energy bend space-time, and everything else moves along the paths created by that curvature. A common illustration involves a stretched sheet of rubber. If you place a heavy ball in the center of the sheet, the surface dips. Smaller objects rolling across the sheet follow curved paths because of that depression. Although this picture is only an analogy, it captures the basic idea that gravity arises from the shape of space-time. Most familiar cosmic objects curve space-time in ways that resemble deep wells. A star, for instance, produces a region where nearby objects naturally move toward it. Black holes represent extreme examples of this curvature. Near a black hole, the distortion becomes so strong that even light cannot escape once it crosses a certain boundary. Cosmic strings bend space too, but in a surprisingly different manner. Instead of creating a deep gravitational well, a cosmic string alters the overall geometry of the region around it, without producing the same kind of inward pull. The effect is subtle, but fascinating. To see how this works, imagine taking a flat sheet of paper and cutting out a very narrow triangular wedge. Once the wedge is removed, bring the two cut edges together and tape them. The surface of the paper is still flat in a small neighbourhood around any point, but the total angle around the centre has changed. The sheet now forms a cone-like shape. If you walk around the tip of that cone, you will complete a full circle sooner than expected because part of the original surface is missing. Space surrounding a cosmic string behaves in a somewhat similar way. The enormous energy stored in the string removes a tiny angular slice from the geometry of space-time. Instead of forming a well like a star does, the string produces what physicists call a deficit angle. Space remains locally flat, but globally it is missing a small wedge. This geometric change affects how objects and light travel nearby. Consider two beams of light approaching the string from opposite sides. In ordinary space, those beams would remain parallel if nothing interfered with them. But near a cosmic string, the geometry of space alters their path slightly. The beams pass on either side of the string and then converge again behind it because the wedge-shaped section of space is missing. For an observer watching from far away, the effect would resemble the light having been split into two paths. If a cosmic string lay between Earth and a distant galaxy, the light from that galaxy could travel around the string on two different sides, and reach us from slightly different directions. Instead of seeing one galaxy, we might see two nearly identical images separated by a small angle in the sky. This phenomenon is a form of gravitational lensing, though it differs from the lensing produced by massive objects like galaxies. Ordinary gravitational lenses bend light gradually, stretching or magnifying images. A cosmic string lens would behave differently. It would produce duplicated images without distorting their shape very much. Both images would look almost exactly the same because the light paths are simply redirected by the altered geometry, rather than stretched by strong curvature. Astronomers have spent years searching for this distinctive signature. Large sky surveys contain millions of galaxies, and researchers examine these images carefully, looking for pairs that might represent the same galaxy viewed along two paths around a cosmic string. Occasionally, astronomers do find galaxies that appear suspiciously similar, but proving that they are actually two images of the same object requires extremely precise measurements. So far, none of the candidates has provided definitive evidence for a cosmic string. Nevertheless, the search continues because the effect would be unmistakable if detected clearly. Beyond lensing, the presence of a cosmic string would also influence nearby matter in subtle ways. Imagine a string moving slowly through a cloud of gas or dust in space. Because the string changes the geometry of space-time, objects on either side of it would experience slightly different trajectories. The result could be a kind of wake behind the moving string where matter becomes concentrated along certain directions. Some early cosmological models suggested that these wakes might help seed the formation of galaxies. As cosmic strings move through the young universe, they could create density variations that later grew into larger structures under the influence of gravity. Later observations of the cosmic microwave background showed that cosmic strings cannot be the primary driver of galaxy formation. However, they could still produce smaller effects that are more difficult to detect. Another fascinating aspect of cosmic strings involves how they move. Unlike rigid rods, cosmic strings would behave more like flexible lines under enormous tension. Segments of string could oscillate, forming waves that travel along their length. When a string oscillates rapidly, it may generate gravitational waves. Gravitational waves are ripples in space-time that travel outward from accelerating masses. They were predicted by Einstein more than a century ago, and were finally detected directly in 2015, when two black holes collided billions of light-years away. Cosmic string loops could produce similar ripples as they oscillate and shrink. Because the tension in the string is so large, even small motions could release significant energy in the form of gravitational radiation. Over time, these waves would carry energy away from the loop, causing it to contract further. Eventually, the loop might disappear completely. The gravitational waves produced during this process could travel across the universe for billions of years. If detectors on Earth are sensitive enough, they might pick up these signals. Several ongoing experiments are searching for such signatures. Observatories like LIGO and Virgo detect high-frequency gravitational waves from compact objects such as merging black holes. Other projects monitor pulsars to detect slower waves passing through our galaxy. Cosmic string loops might produce signals that fall somewhere within these detection ranges. If such signals were discovered, they could provide strong evidence that cosmic strings exist. The unusual geometry surrounding a cosmic string leads to another interesting consequence. Because space around the string contains a missing wedge, two objects moving toward each other on opposite sides of the string could suddenly appear closer together than expected once they passed the string. In theory, this effect could produce sudden shifts in the positions of distant stars or galaxies. These shifts would be extremely small and difficult to measure, but advanced instruments might one day detect them. Despite all these possibilities, it is important to remember that cosmic strings remain hypothetical. No confirmed observation has yet demonstrated their existence. Still, their predicted behavior fits naturally within many theories describing the early universe. The mathematics describing topological defects appears in several models of high-energy physics, and cosmic strings emerge as a possible consequence. If they do exist, They would represent some of the oldest surviving features in the cosmos. Their presence would reveal information about conditions that existed during the earliest fractions of a second after cosmic expansion began. The idea that a line thinner than an atom could reshape the geometry of space across vast distances may seem extraordinary, but modern physics often leads us to conclusions that challenge everyday intuition. Space is not merely a passive stage on which cosmic events occur. It is an active participant, capable of bending, stretching, and responding to the energy within it. Cosmic strings illustrate that principle in a particularly striking way. They show how a narrow concentration of energy can alter the paths of light, reshape the geometry of space-time, and send ripples travelling across the universe. If cosmic strings can bend the paths of light so dramatically, what might we actually see when we observe the distant universe through one of these invisible threads? Look out across the night sky with a telescope, and what appears at first to be a calm and steady universe begins to reveal surprising tricks of light. Astronomers often see galaxies stretched into long arcs, distant quasars appearing multiple times in the same patch of sky, and clusters of galaxies bending the light of objects far behind them. These effects are not illusions created by telescopes. They are the result of gravity changing the paths that light follows through space. This phenomenon is known as gravitational lensing. The basic idea comes from general relativity. When mass or energy is present, space-time curves. Light always travels along the straightest possible path through that curved space-time. Because the geometry is altered, those paths may appear bent from the perspective of a distant observer. Massive galaxies and clusters act like giant cosmic lenses. They distort the images of objects located far behind them. Sometimes the background galaxy is stretched into a curved arc. In other cases, multiple images of the same object appear around the lensing mass. These gravitational lenses have become powerful tools in astronomy. By studying how light bends, scientists can measure the distribution of mass in galaxies and clusters, including the invisible component known as dark matter. Cosmic strings, if they exist, would create a different kind of gravitational lens. Unlike galaxies or black holes, a cosmic string does not produce a deep gravitational well. Instead, as discussed earlier, the string removes a small wedge from the geometry of space-time. The surrounding region remains locally flat, but the total angle around the string is slightly reduced. This effect leads to an unusual form of lensing. To understand it, imagine once again a flat sheet of paper. Suppose you remove a narrow triangular slice and tape the remaining edges together. The sheet still appears flat in most places, but a small portion of the original surface is missing. Now draw two straight lines on the paper approaching the taped seam from opposite directions. Because the wedge has been removed, the lines may meet sooner than expected. Light behaves similarly near a cosmic string. If a beam of light passes on one side of the string and another beam passes on the other side, the two paths may converge as they continue through space. An observer receiving that light could see two images of the same distant object. The remarkable part is how clean those images would appear. In ordinary gravitational lensing, massive objects distort the image of the background source. The light rays follow curved paths through strongly warped space-time, stretching the image into arcs or rings. Cosmic string lensing works differently. Because the space around the string is mostly flat except for the missing wedge, the light does not experience the same kind of distortion. Instead, it simply travels along two slightly different straight paths that converge behind the string. As a result, the observer would see two identical images of the same galaxy or quasar, positioned side by side. Both images would have nearly the same brightness and shape. They would look almost like perfect duplicates. This duplication would be the key observational signature of a cosmic string, acting as a gravitational lens. Astronomers have searched for such pairs in deep sky surveys. Modern telescopes capture enormous images containing millions of galaxies. Within these data sets, researchers look for pairs of galaxies that appear nearly identical and separated by a small angular distance. If the two galaxies truly are the same object seen along two paths around a cosmic string, they should share the same spectral features, the same brightness patterns, and the same internal structure. Several candidate pairs have been studied over the years. One example that briefly attracted attention involved two galaxies that appeared strikingly similar in shape and brightness. For a time, some researchers suggested they might be images produced by a cosmic string lens. Further analysis, however, showed that the galaxies were actually two separate objects that happened to resemble each other. Cases like this demonstrate how difficult it can be to confirm the presence of a cosmic string. Even though the predicted lensing effect is distinctive, the universe contains so many galaxies that coincidences can occur. Two unrelated galaxies might look similar simply by chance. To identify a genuine cosmic string lens, astronomers would need extremely precise observations. One important clue would involve the alignment of the duplicated images. Because a cosmic string produces a deficit angle in spacetime, the pair of images would appear along a straight line perpendicular to the direction of the string. If several background objects were lensed by the same string, their duplicated images would form a series of pairs aligned along a narrow strip in the sky. Finding such a pattern would provide strong evidence for the presence of a cosmic string. Future astronomical surveys may improve the chances of detecting this effect. Projects like the Vera-Rubin Observatory and other large sky mapping programs will photograph vast regions of the universe with unprecedented detail. These surveys will catalogue billions of galaxies. Within such enormous datasets, even rare phenomena like cosmic string lensing might finally be observed. Another possible signature involves slight shifts in the positions of objects as a cosmic string moves. Unlike galaxies, which remain relatively stationary over human timescales, a cosmic string might move through space at high speed. If a string passed in front of a distant star or galaxy, the duplication effect could appear briefly and then disappear as the string moved away. Astronomers monitoring the sky carefully might detect these temporary duplications. The idea may sound dramatic, but the effect would still be subtle. The angular separation between the images might be extremely small, requiring high-resolution instruments to detect. Beyond visible light, cosmic strings could also influence other signals travelling through the universe. For instance, radio waves emitted by distant quasars could follow multiple paths around a string, creating interference patterns that reveal the presence of the deficit angle in spacetime. Careful measurements of radio signals might therefore provide another method for searching for cosmic strings. There is also the possibility that strings could affect the cosmic microwave background radiation. This faint glow of microwave light fills the universe and represents the oldest light we can observe. It was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely. If a cosmic string passed through this radiation field, it might produce slight temperature discontinuities along its path. These discontinuities would appear as narrow lines in maps of the cosmic microwave background. Researchers have examined high-precision maps from satellites such as WMAP and Planck, looking for such patterns. So far, no definitive cosmic string signatures have been found, but the data continue to be analysed with increasingly sophisticated techniques. The concept of cosmic string lensing also leads to an interesting thought experiment. Imagine observing a distant galaxy through a powerful telescope. At first, you see a single spiral galaxy glowing faintly in the darkness. Then, as a cosmic string drifts between you and the galaxy, the image suddenly splits into two identical spirals separated by a small distance. For a brief period, the sky would appear to contain a perfect duplicate of that galaxy. As the string continues moving, the two images would merge again into one. Although the probability of witnessing such an event is extremely low, it illustrates how dramatically cosmic strings could influence light travelling across the universe. The study of gravitational lensing has already revealed many hidden aspects of the cosmos, including the distribution of dark matter and the existence of distant galaxies that would otherwise remain invisible. If cosmic strings exist, they could become another fascinating lens through which we explore the universe. Their lensing effect would not magnify or distort the background objects in the usual way. Instead, it would duplicate them, revealing the subtle geometric changes introduced by the presence of the string. Such a discovery would do more than confirm a long-standing theoretical prediction. It would provide direct evidence that the early universe underwent phase transitions capable of producing topological defects. It would connect observations of distant galaxies with the physics of the universe during its first fractions of a second. Long before scientists could detect them, gravitational waves existed only as a prediction hidden inside the mathematics of Einstein's equations. When Einstein first described general relativity in 1915, he showed that mass and energy could bend spacetime, changing the paths that objects follow. A few years later, he realized something even more remarkable. If massive objects moved in certain ways, the curvature of spacetime itself could ripple outward like waves spreading across water. These ripples are known as gravitational waves. Unlike ordinary waves in water or air, gravitational waves do not travel through a material medium. They are disturbances in space-time itself. As a gravitational wave passes through a region of space, it stretches distances slightly in one direction while compressing them in another. The effect is extremely small. Even powerful gravitational waves from dramatic cosmic events change distances by far less than the width of an atomic nucleus. For many decades after Einstein predicted them, gravitational waves remained purely theoretical because detecting such tiny distortions seemed nearly impossible, but technology gradually improved. By the early 21st century, physicists had built instruments sensitive enough to measure these incredibly subtle changes. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves. The signal came from two black holes spiraling together and merging more than 1 billion light-years away. The event confirmed that gravitational waves are real, and that space-time itself can vibrate when massive objects accelerate. Since then, several more detections have followed, involving black holes and neutron stars colliding in distant regions of the universe. These discoveries opened an entirely new way of observing the cosmos. Instead of studying light alone, scientists can now listen to the faint vibrations of space-time itself. Cosmic strings, if they exist, could also generate gravitational waves. The reason lies in the enormous tension stored along these strings. As described earlier, a cosmic string behaves somewhat like an extremely tight elastic band. Any disturbance along its length can produce oscillations that travel along the string. When a segment of string vibrates or moves rapidly, the energy involved can disturb spacetime around it. That disturbance spreads outward as a gravitational wave. One of the most important sources of these waves would be cosmic string loops. Cosmic strings are expected to form long segments stretching across space, but when two segments intersect, they can reconnect and create closed loops. These loops behave like flexible rings under intense tension. Because the tension constantly pulls inward, the loop begins to contract and oscillate. During this motion, parts of the loop move at extremely high speeds. In certain regions of the loop, called cusps, the string briefly approaches the speed of light. These rapid motions can generate bursts of gravitational radiation. Another interesting feature of oscillating loops is the formation of kinks. A kink occurs when two segments of string reconnect and create a sharp corner in the loop. As the loop oscillates, this corner travels along the string, producing additional bursts of gravitational waves. Over time, the loop gradually loses energy through this radiation. As energy escapes, the loop shrinks, becoming smaller and smaller until it eventually disappears. During its lifetime, however, it may produce many pulses of gravitational waves. These signals could travel across the universe for billions of years before reaching detectors on Earth. Because cosmic string loops could form at many different sizes, The gravitational waves they produce might span a wide range of frequencies. Some signals might fall within the range detectable by instruments like LIGO or Virgo. Others might produce much slower waves detectable through entirely different techniques. One of those techniques involves monitoring pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles. As the star spins, the beam sweeps across space like a lighthouse. When the beam passes Earth, radio telescopes detect a pulse. Many pulsars rotate with astonishing regularity, producing pulses with predictable timing. Astronomers can measure the arrival time of each pulse with extraordinary precision. If a gravitational wave passes between Earth and the pulsar, it slightly stretches or compresses the space along that path. This changes the travel time of the radio signal by a tiny amount. By monitoring networks of pulsars scattered across the sky, scientists can search for correlated timing shifts that indicate gravitational waves passing through our region of the galaxy. This technique is known as a pulsar timing array. Several international collaborations are currently using pulsar timing arrays to search for very low-frequency gravitational waves. These waves have periods measured in years rather than milliseconds. Cosmic strings could produce signals within this range, particularly if large loops formed early in the history of the universe. Another potential source of gravitational radiation from cosmic strings involves collisions between strings themselves. When two strings intersect and reconnect, the process can release energy into spacetime. The resulting vibrations may produce gravitational waves that propagate outward. These events would be rare but potentially detectable if the strings carry enough energy. The pattern of gravitational waves produced by cosmic strings would differ from those generated by black hole mergers. Instead of a single dramatic burst followed by silence, cosmic strings might create a background of many overlapping signals. Physicists sometimes refer to this as a stochastic gravitational wave background. Imagine standing in a busy city and listening to the distant hum of traffic. You cannot identify each individual car, but you can hear the combined sound of many vehicles moving through the streets. In a similar way, detectors might one day observe a faint background vibration created by countless cosmic string loops oscillating across the universe. Detecting such a signal would be extremely exciting. It would suggest that the universe contains a network of cosmic strings continuously producing gravitational waves. The properties of the signal could reveal information about the tension of the strings and the energy scale at which they formed. This information would connect directly to theories describing the earliest moments of the universe. Some predictions suggest that gravitational waves from cosmic strings might be among the strongest signals in certain frequency ranges. Future detectors could therefore play a key role in confirming whether these structures exist. Several next-generation observatories are currently under development. One example is the Laser Interferometer Space Antenna, or LISA. Unlike ground-based detectors, LISA will operate in space, using 3 spacecraft arranged in a triangular formation millions of kilometers apart. This configuration will allow the instrument to detect gravitational waves with lower frequencies than those accessible from Earth. Cosmic string loops could produce signals within this frequency band, making LISA an important tool in the search for these objects. Other experiments will continue monitoring pulsars and improving ground-based detectors, gradually expanding our ability to listen to the universe. Even if cosmic strings are rare, their gravitational waves might still reach us from distant parts of the cosmos. These signals would carry information about events that occurred billions of years ago, when the universe was much younger. The possibility that space-time might still be vibrating from the motion of ancient cosmic strings is a fascinating one. It suggests that the universe is not only filled with light from distant stars and galaxies, but also with faint echoes of events that happened shortly after the Big Bang. Those echoes travel silently through space, stretching and compressing distances by tiny amounts. With the right instruments, we may eventually detect them, and if we do, the signals could reveal far more than just the presence of cosmic strings. They might also tell us where to look for the invisible threads themselves, hidden among the vast structures of the universe. Astronomers are accustomed to searching for objects that emit light. Stars glow because nuclear reactions heat their surfaces. Galaxies shine because billions of stars combine their light. Even distant clouds of gas become visible when nearby stars excite the atoms within them. For most of the history of astronomy, the rule was simple. If something exists in the universe, it probably produces some form of light that telescopes can detect. Cosmic strings do not follow that rule. If these objects exist, they would not shine, glow, or radiate in the familiar way that stars and galaxies do. A cosmic string is not made of atoms that can heat up and emit photons. Instead, it is a narrow region where enormous energy remains trapped in a field configuration. Because of that, it would be almost perfectly invisible to ordinary telescopes. This creates an interesting challenge. Detecting something that does not emit light requires indirect methods. Astronomers must look for the effects the object has on its surroundings rather than the object itself. In the case of cosmic strings, those effects arise mainly from gravity and from the motion of the strings as they evolve over time. One of the first strategies scientists considered involves gravitational lensing. As described earlier, a cosmic string changes the geometry of spacetime around it by removing a small wedge from the surrounding space. Light passing on opposite sides of the string can follow slightly different paths and reach an observer from two directions. The result would be two nearly identical images of the same distant object. Astronomers search for this phenomenon by examining large surveys of galaxies and quasars. Modern telescopes photograph vast regions of the sky, containing millions or even billions of objects. Computer algorithms then scan these images, looking for pairs of galaxies that appear remarkably similar. If two images have nearly identical shapes, brightness patterns, and spectral signatures, they might represent the same object whose light has been split by a cosmic string. The difficulty lies in distinguishing genuine duplication from coincidence. The universe contains an enormous number of galaxies. Some of them naturally resemble each other. Two spiral galaxies may look almost identical, simply because many galaxies share similar structures. To confirm that two images come from the same object, astronomers must measure their spectra in detail. A spectrum reveals the chemical composition, motion, and distance of a galaxy by analysing the light it emits. If two images truly originate from the same source, their spectra should match extremely closely. Even with careful analysis, proving the presence of a cosmic string lens remains challenging. So far, no observation has provided definitive evidence. Nevertheless, each new survey increases the chances of finding such a signal. The next generation of sky surveys will be especially powerful in this search. Observatories such as the Vera Rubin Observatory will repeatedly photograph the entire visible sky over many years. This project will create a massive archive of images tracking how the sky changes over time. With such detailed observations, astronomers might detect temporary lensing events caused by a moving cosmic string. If a string passed between Earth and a distant galaxy, the image of that galaxy might split briefly into two copies before merging again once the string moved away. Another approach to detecting cosmic strings involves the cosmic microwave background. The cosmic microwave background, often abbreviated as the CMB, is the faint radiation left over from the early universe. It fills all of space and represents light released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. Satellites such as WMAP and Planck have mapped the temperature of this radiation with extraordinary precision. These maps show tiny variations in temperature across the sky, reflecting density fluctuations present in the early universe. If cosmic strings existed at that time, they could leave distinctive patterns in the microwave background. As a string moves through space, it alters the geometry of space-time around it. Photons travelling past a string may experience slight shifts in energy due to this changing geometry. This effect, known as the Kaiser-Stebbins effect, would produce narrow lines in the CMB temperature map where the radiation appears slightly hotter on one side of the string and slightly cooler on the other. Detecting these patterns requires extremely precise measurements because the temperature differences are tiny. Researchers have examined the most detailed CMB maps available, searching for linear discontinuities that might indicate a cosmic string. Although several studies have placed limits on how many strings could exist, none has yet found a clear signal. Another promising method involves gravitational waves. As discussed earlier, cosmic string loops could oscillate and release energy in the form of gravitational radiation. These ripples in space-time might travel across the universe for billions of years before reaching Earth. Gravitational wave detectors are designed to measure incredibly small changes in distance caused by passing waves. Instruments like LIGO use laser beams travelling along long arms to detect distortions smaller than the width of a proton. If a cosmic string loop produced a burst of gravitational waves, detectors might capture the signal. Such bursts would have distinctive shapes that differ from those produced by merging black holes or neutron stars. By analysing the waveform carefully, scientists could identify the source of the signal. In addition to individual bursts, cosmic strings might produce a continuous background of gravitational waves generated by many loops oscillating across the universe. Detecting this background requires long-term monitoring and extremely sensitive instruments. Pulsar timing arrays, which track the regular pulses of rotating neutron stars, provide one method for detecting such signals. When a gravitational wave passes between Earth and a pulsar, it slightly changes the arrival time of the pulses. By measuring these variations across many pulsars, scientists can search for correlated signals indicating gravitational waves passing through the galaxy. Recently, several pulsar timing collaborations have reported evidence for a low-frequency gravitational wave background. Although the most likely source appears to be supermassive black hole binaries, researchers are also exploring whether cosmic strings might contribute to the signal. Beyond gravitational waves and lensing, cosmic strings could influence the distribution of matter in subtle ways. A moving string could create a wake behind it, drawing matter together along certain directions. These wakes might leave faint imprints in the large-scale structure of galaxies. Studying these effects requires detailed simulations of cosmic string networks, combined with observations of galaxy distributions. Although the signatures are subtle, improved observations may reveal patterns consistent with the presence of strings. The search for cosmic strings also benefits from advances in computing. Simulating the evolution of a cosmic string network across billions of years is a complex problem. The strings move, oscillate, reconnect, and form loops, all while the universe expands around them. High-performance computers allow physicists to model these processes and predict what observable signals might look like. These predictions guide observational campaigns by identifying the most promising signatures to search for. Despite decades of effort, cosmic strings remain hypothetical. That does not mean the search has failed. On the contrary, each new experiment narrows the range of possibilities. Observations place limits on how many strings could exist and how strong their tension might be. These limits help refine theoretical models of the early universe. If cosmic strings formed during a grand unified phase transition, their tension would be extremely high. Current observations already rule out some versions of those models. Other theories predict lighter strings that would produce weaker signals, making them harder to detect but still possible. The process of hunting these invisible threads therefore involves both observation and theory. Astronomers collect vast amounts of data from telescopes, gravitational wave detectors, and cosmic background surveys. Physicists analyze that data, searching for patterns that match the predictions of cosmic string models. If a clear signal appears, it would represent one of the most remarkable discoveries in cosmology. It would show that the universe still contains structures formed during its earliest moments, preserved across billions of years of cosmic expansion. Until that moment arrives, the search continues. A faint glow fills the entire universe, even in regions where there are no stars, no galaxies, and no obvious sources of light. This glow cannot be seen with human eyes because it lies in the microwave part of the electromagnetic spectrum, but sensitive radio telescopes can detect it easily. It arrives from every direction in the sky with remarkable uniformity. Wherever astronomers point their instruments, they find the same quiet background signal. This radiation is known as the cosmic microwave background, often abbreviated as the CMB. The discovery of this signal in 1965 was one of the most important moments in modern cosmology. Two radio astronomers, Arno Penzias and Robert Wilson, were working with a large antenna designed for satellite communication experiments. No matter how carefully they adjusted their equipment, they kept detecting a persistent background noise that seemed to come from all directions equally. At first they suspected a technical problem. They checked the electronics, cleaned the antenna, and even removed pigeons that had nested inside the instrument. Yet the signal remained. Around the same time, a separate group of physicists had been predicting that the early universe should have left behind a faint glow of radiation as it cooled. When the two groups compared their findings, it became clear that the mysterious noise detected by the antenna was actually ancient light from the early universe. The cosmic microwave background is essentially a snapshot of the universe when it was about 380,000 years old. Before that time, the universe was filled with a hot plasma of electrons and atomic nuclei. Photons, which are particles of light, constantly scattered off these charged particles. Because of this scattering, light could not travel freely. The universe was opaque, somewhat like the interior of a dense fog. As the universe expanded and cooled, conditions eventually became calm enough for electrons to combine with atomic nuclei to form neutral atoms. When this happened, photons no longer scattered constantly. They began travelling freely through space. The radiation released during that moment still fills the universe today. As the universe expanded over billions of years, the wavelength of that radiation stretched, shifting it into the microwave region of the spectrum. What makes the CMB especially useful for cosmologists is its remarkable uniformity. The temperature of this radiation is almost exactly the same in every direction, about 2.7 degrees above absolute zero. Yet the word almost is important here. Careful measurements reveal tiny variations in temperature across the sky, differences of only a few millionths of a degree. These variations reflect slight differences in density present in the early universe. Regions that were slightly denser eventually attracted more matter through gravity, leading to the formation of galaxies and clusters of galaxies. In this way, the cosmic microwave background contains a map of the initial conditions from which the large-scale structure of the universe grew. Because the CMB provides such a detailed picture of the early universe, it also offers a way to search for unusual phenomena that may have occurred during that time. Cosmic strings are one of the possibilities researchers have investigated. If cosmic strings existed when the CMB radiation was released, they could leave subtle imprints in the temperature pattern we observe today. To understand how this might happen, imagine a cosmic string moving through space while the CMB photons travel past it. As discussed earlier, the presence of the string alters the geometry of space-time by removing a small angular wedge from the surrounding region. Photons passing on one side of the string travel along slightly different paths than photons passing on the other side. If the string is moving relative to the background radiation, this geometry change produces a small shift in the energy of the photons. Photons on one side of the string may appear slightly hotter, while those on the other side appear slightly cooler. The result is a narrow line across the CMB map where the temperature suddenly changes by a small amount. This effect is called the Kaiser-Stebbins effect, named after the physicists who studied how cosmic strings might influence the cosmic microwave background. In a temperature map of the sky, such a feature would appear as a straight discontinuity. On one side of the line, the radiation would be just a tiny bit warmer. On the other side, it would be slightly cooler. The difference would be extremely small, but modern instruments are capable of measuring temperature variations in the CMB with remarkable precision. Over the past several decades, a series of increasingly sophisticated experiments have mapped the microwave background in great detail. The COBE satellite, launched in 1989, first detected the tiny temperature variations predicted by cosmologists. Later missions such as WMAP and the Planck satellite produced much higher resolution maps of the sky. These maps reveal the delicate pattern of fluctuations that seeded the formation of galaxies. Researchers have examined these maps carefully, looking for straight-line features that might indicate the presence of cosmic strings. The task is difficult because the temperature fluctuations caused by ordinary density variations also produce complex patterns. Distinguishing a cosmic string signature from random fluctuations requires careful statistical analysis. So far, no unmistakable string pattern has been found. However, the absence of clear evidence still provides useful information. By analysing the CMB data, scientists can estimate how strong cosmic strings could be without producing detectable signals. These measurements place limits on the tension of possible strings and on how many could exist within the observable universe. In other words, even when cosmic strings are not observed directly, the data helps narrow down the possibilities. Another interesting feature of the cosmic microwave background involves polarization. Light waves can vibrate in different orientations as they travel. When many photons share a similar orientation, the radiation is said to be polarized. The CMB radiation contains faint patterns of polarization created during the early universe. These patterns arise from interactions between photons and electrons just before the radiation began traveling freely through space. Certain cosmological events can influence these polarization patterns. Cosmic strings could potentially produce characteristic polarization signatures along the same narrow lines where temperature discontinuities appear. Detecting such signals would require extremely sensitive instruments, but future experiments may achieve the necessary precision. The cosmic microwave background therefore acts like a historical record of the universe's early conditions. It preserves information about processes that occurred long before the first stars formed. By studying its patterns carefully, cosmologists can test theories about inflation, dark matter, and the formation of large-scale structures. Cosmic strings are part of that investigation. If they existed during the era when the CMB radiation was released, their presence might still be encoded in the temperature and polarization maps we observe today. Even though the signals would be subtle, they could provide valuable clues about the behavior of fields and forces during the universe's earliest moments. The search for these clues continues as new observations improve our ability to measure the CMB. Future missions may produce maps with even greater resolution and sensitivity. With better data, researchers will be able to examine smaller and smaller features in the radiation background. If cosmic strings left even faint traces in the microwave sky, those traces might eventually become visible. The cosmic microwave background is often described as the oldest light we can observe. It has travelled across the universe for more than 13 billion years, carrying with it information about the conditions present when the universe was still very young. Hidden within that ancient light could be subtle hints of structures formed during the earliest phase transitions of the cosmos. Out in the enormous distances between galaxies, if cosmic strings exist, they would not simply lie quietly in place forever. These objects, despite being incredibly thin, would carry enormous tension. That tension would constantly influence their motion, pulling them into straighter shapes and causing them to shift gradually through space as the universe expands. Because of this motion, strings that stretch across cosmic distances could eventually encounter one another. When people first imagine two strings colliding, they often picture them passing through each other like threads sliding past in mid-air. But theoretical studies suggest something more interesting might happen. Instead of simply crossing without interaction, cosmic strings are expected to reconnect. Physicists call this process intercommutation. When two segments of string approach and intersect, the field configurations that define them can rearrange themselves, the strings effectively exchange partners, cutting and reconnecting in a new pattern. If you imagine two pieces of thread crossing and then swapping ends, you have a rough idea of what this process looks like. The reconnection is not caused by friction or contact in the ordinary sense. Remember that cosmic strings are not made of atoms or material fibers. They are topological defects in fields that fill space. When two such defects intersect, the field surrounding them must reorganize. In many models, the most energetically favorable outcome is for the strings to reconnect. This simple process has important consequences for how cosmic string networks evolve over time. Early in the universe, if strings formed during phase transitions, there may have been many of them stretching across space in different directions. As the universe expanded, those strings would move relative to one another. Eventually, some of them would intersect. Each time two strings reconnected, the overall structure of the network would change. Sometimes a long string crossing another long string would simply exchange segments and continue stretching across space. But in other situations, the reconnection could create closed loops. Imagine a long string crossing another segment that forms a small kink. When they reconnect, a piece of the string may detach, forming a loop that no longer connects to the larger network. These loops play a major role in the evolution of cosmic string systems. Once a loop forms, it behaves like a flexible ring under enormous tension. The tension pulls inward, causing the loop to oscillate. As it oscillates, parts of the string accelerate rapidly. These motions release energy in the form of gravitational waves. Over time, the loop shrinks as it loses energy, gradually becoming smaller until it eventually disappears entirely. This process acts like a kind of cosmic recycling system. Long strings reconnect, creating loops, and those loops slowly evaporate through gravitational radiation. Because of this mechanism, the total amount of string in the universe does not grow uncontrollably. Instead, the network evolves toward a balance between long strings and loops. Computer simulations have helped scientists understand how this balance might work. Researchers model large regions of the universe containing many cosmic strings. As the simulation runs, the strings move, intersect, reconnect, and produce loops. The overall pattern begins to settle into a state where the average number of long strings per region remains roughly constant even as the universe expands. This behavior is sometimes called scaling. In a scaling network, the typical distance between long strings grows in proportion to the size of the universe itself. The network does not become denser or thinner relative to cosmic expansion. Loops continue to form and disappear, maintaining the overall balance. The reconnection process also creates distinctive features along the strings. When two strings reconnect, the point where they join often produces a sharp bend called a kink. This kink then travels along the string at nearly the speed of light. As the kink moves, it creates small disturbances in the surrounding spacetime. These disturbances can generate additional bursts of gravitational waves. In some cases, a loop may develop points known as cusps. A cusp occurs when part of the loop briefly moves at extremely high velocity, approaching the speed of light. At that instant, the string doubles back on itself, concentrating energy into a very small region. Cusps are predicted to produce intense, short bursts of gravitational radiation. Detecting such bursts would be one of the possible ways astronomers might confirm the existence of cosmic strings. Another consequence of string collisions involves the formation of increasingly complex networks. In regions where many strings intersect, reconnections can produce a tangled pattern of segments and loops. Over time, however, tension tends to simplify the structure by straightening segments and removing excess loops through radiation. Despite the enormous scales involved, the mathematics describing this evolution shares similarities with other physical systems. For example, networks of vortex lines in superfluids or defects in certain crystals show comparable behavior. In those systems, defects move, reconnect, and gradually simplify their configuration over time. Cosmic strings operate under far more extreme conditions, but the underlying principles remain related. The study of these processes requires advanced simulations because direct observation is not currently possible. Physicists must calculate how strings move through expanding space-time, how often they reconnect, and how quickly loops radiate energy. These simulations help predict the types of signals astronomers might detect. For instance, a network of cosmic strings producing many loops would generate a background of gravitational waves spread across a range of frequencies. Occasional reconnection events might create sudden bursts that stand out above the background. Observatories designed to detect gravitational waves are therefore an important part of the search for cosmic strings. Another interesting possibility arises when strings intersect repeatedly over long periods. If a loop encounters another string or another loop, additional reconnections may occur. This can break the loop into smaller loops or attach it back to the network. The result is a dynamic system where strings constantly change their shapes and connections. Although these events occur across enormous distances and over very long timescales, their effects accumulate. Over billions of years, the motion and collisions of cosmic strings could produce countless loops, bursts of gravitational radiation, and subtle changes in the structure of space-time. Yet even with all this activity, the strings themselves remain extremely difficult to observe directly. Their thickness is far too small for any telescope to resolve, and they emit very little electromagnetic radiation. Most of their influence appears indirectly through gravity. Still, the possibility that invisible threads might stretch across cosmic distances, occasionally intersecting and exchanging segments, adds an unexpected layer of complexity to the universe. Instead of a perfectly smooth expanse of space, the cosmos might contain a network of ancient structures quietly evolving over billions of years. A closed loop of cosmic string would not sit quietly in space like a rigid ring. The moment such a loop formed, the enormous tension along the string would begin pulling inward. This tension behaves somewhat like the force in a stretched rubber band, except vastly stronger. As a result, the loop would immediately start moving and oscillating. The simplest way to picture this is to imagine a rubber band that has been flicked into the air. It stretches, twists, and vibrates as the tension pulls different parts of it in various directions. Now imagine that same behavior happening in space, but with a loop so thin that its width is far smaller than a proton, and with tension strong enough to influence space-time itself. That is roughly how a cosmic string loop would behave. When a loop forms through the reconnection of two string segments, it contains bends and irregularities along its length. These bends travel along the string as waves. The tension pulls the loop inward, while the waves move around the loop's circumference. Because of these motions, the loop does not remain perfectly circular. It stretches into different shapes as waves propagate along it. Portions of the string may move very quickly, sometimes approaching the speed of light. These rapid motions are important because accelerating masses generate gravitational waves. Each time the loop oscillates, it disturbs the surrounding space-time slightly. Those disturbances propagate outward as ripples travelling through the universe. Over time, the loop loses energy through this radiation. The loss of energy causes the loop to shrink gradually. At first, the change may be slow. The loop might oscillate for long periods while slowly becoming smaller. But eventually the loop radiates enough energy that its size decreases significantly. The oscillations continue until the loop becomes extremely small and finally disappears. During its lifetime, however, the loop can produce many bursts of gravitational radiation. Some of the most intense signals occur at special points along the string known as cusps. A cusp forms when part of the loop moves so quickly that the string briefly folds back on itself. At that moment, a small section of the string reaches velocities extremely close to the speed of light. The energy concentrated in that region becomes enormous. When the cusp forms and disappears, it sends out a sharp burst of gravitational waves. These bursts are predicted to be strong enough that future gravitational wave detectors might observe them if cosmic strings exist within the observable universe. Another feature that can appear along oscillating loops is called a kink. Kinks form during the reconnection process when two strings intersect and exchange segments. The reconnection creates a sharp corner in the string. This corner then travels along the loop as a disturbance. Each time the kink moves through the loop, it generates additional gravitational waves. Although the waves from individual kinks may be weaker than those from cusps, they can still contribute to the overall gravitational radiation emitted by the loop. Over cosmic timescales, many loops could form and evolve simultaneously across the universe. Some loops might be relatively small, perhaps only a few kilometers in length. Others could be much larger, spanning distances comparable to the size of a galaxy. Regardless of their size, all loops follow the same basic pattern. They oscillate, radiate energy, and gradually shrink. This process has led physicists to describe cosmic string loops as objects that ring the universe. The comparison comes from the way their oscillations generate gravitational waves in a manner somewhat similar to how a vibrating bell produces sound waves. A bell vibrates when struck, sending sound waves outward through the air. A cosmic string loop vibrates because of its tension, sending gravitational waves outward through spacetime. The analogy is not perfect, but it captures the idea that loops act like sources of repeating signals. Those signals may travel across vast distances for billions of years before reaching Earth. Because loops could form throughout the history of the universe, their gravitational radiation might combine into a persistent background signal. Imagine listening to distant music drifting across a city at night. Individual instruments may be impossible to identify, but the combined sound creates a faint, continuous hum. In a similar way, countless cosmic string loops oscillating throughout the universe could produce a gravitational wave background. Detecting such a background is one of the goals of modern gravitational wave astronomy. Current detectors like LIGO are sensitive to relatively high-frequency waves produced by compact objects such as merging black holes. Cosmic string loops might produce signals across a broader range of frequencies. Some loops could emit waves detectable by ground-based interferometers. Others might generate slower waves that could be observed using pulsar timing arrays or future space-based observatories. One planned mission that may help explore this possibility is the Laser Interferometer Space Antenna, or LISA. Unlike ground-based detectors, LISA will consist of 3 spacecraft separated by millions of kilometers, forming a triangular interferometer in space. This configuration will allow the mission to detect gravitational waves with lower frequencies than those accessible on Earth. If cosmic string loops exist in sufficient numbers, their oscillations could produce signals within LISA's sensitivity range. Another aspect of loops that interests physicists involves how they interact with the surrounding universe. Because loops carry enormous energy, their gravitational effects might influence nearby matter. In most cases, these effects would be extremely small, but in certain situations they could produce subtle distortions in the distribution of matter. For example, a large loop moving through space might slightly alter the paths of nearby particles or radiation. These effects would be difficult to detect, but they contribute to the overall gravitational signature of cosmic strings. The lifetime of a loop depends on its size and the tension of the string. Larger loops contain more energy and may take longer to radiate it away. Smaller loops lose energy more quickly and disappear sooner. Some loops might survive for millions or even billions of years before shrinking completely. During that time, they would continue oscillating and emitting gravitational waves. If cosmic strings formed during the earliest moments of the universe, the creation of loops may have been happening ever since. Each reconnection between long strings could generate new loops that join the cosmic population. This ongoing process would mean that loops could exist throughout the universe today. They would be invisible in ordinary light, but their gravitational radiation could still travel across space, carrying information about their motion. Listening for these signals is one of the ways scientists hope to uncover evidence of cosmic strings. If detectors eventually identify the characteristic pattern expected from oscillating loops, It would provide strong support for the idea that the universe contains these ancient defects. Such a discovery would reveal that the cosmos is not entirely smooth beneath its vast distances. Hidden within it could be countless tiny rings of energy vibrating quietly, sending ripples through space-time as they slowly shrink and disappear. And once we start imagining these invisible loops scattered across the universe, another question naturally comes to mind. If a cosmic string loop can oscillate and radiate energy on such enormous scales, what might happen if one of these objects ever passed near our own planet? Imagine just for a moment that somewhere in the vastness of the universe a cosmic string drifts slowly through space. It stretches across unimaginable distances, thinner than any particle we can observe directly, yet carrying enormous energy along its length. For billions of years it may have travelled through the expanding cosmos, moving quietly between galaxies and clusters. Now suppose that, by an extraordinary coincidence, a segment of such a string happened to pass near our planet. At first, this idea may sound like the beginning of a dramatic science fiction scenario. A mysterious thread from the early universe approaches Earth, carrying enough energy to rival mountains compressed into a line. It seems natural to wonder whether such an encounter would be catastrophic. Interestingly, theoretical studies suggest that the situation would be much stranger than destructive. The first thing to remember is how incredibly thin a cosmic string would be. Even though it could stretch across astronomical distances, its width might be far smaller than the size of a proton. That means the string would occupy an almost unimaginably tiny region of space. If a cosmic string passed through Earth, the actual area of contact would be microscopic. Unlike an asteroid or comet, the string would not slam into the planet with a visible impact. It would not produce a fiery explosion or a crater in the ground. There would be no object made of matter striking the surface. Instead, the string would simply move through space, carrying its unusual gravitational geometry along with it. The primary effect of a cosmic string comes from the deficit angle it creates in space-time. As discussed earlier, the presence of the string removes a small wedge from the geometry of the surrounding region. Space remains locally flat, but globally it contains a slight discontinuity. If the string moved through Earth, this geometric distortion would move with it. To understand what that might mean in practical terms, imagine two objects located on opposite sides of the string as it passes between them. Because the wedge of space is missing, the distance between those objects could change suddenly. From the perspective of observers, it would appear as though the objects had shifted position relative to one another. The effect would be subtle but potentially noticeable if the string moved quickly enough. Consider two people standing several meters apart. If a cosmic string passed between them, the geometry of space might cause the distance between them to shrink slightly for a brief moment, before returning to normal once the string moved away. They would not feel a push or pull in the usual sense. Instead, the change would arise from the altered geometry of space-time. In reality, such shifts would likely be extremely small, because the deficit angle associated with most theoretical cosmic strings is predicted to be tiny. Another consequence of the string's motion could involve the paths of light. Light travelling on either side of the string follows slightly different routes because of the missing wedge of space. As the string moved through Earth's vicinity, distant stars might briefly appear doubled in the sky. Observers could see two identical images of a star separated by a very small angle. As the string continued moving, the images would merge back into one. This duplication effect would last only while the string lay between the observer and the star. Because cosmic strings are expected to move at relativistic speeds, the entire event might last only seconds or minutes. Detecting such a phenomenon would require extremely precise instruments capable of monitoring tiny changes in the positions of stars. Another theoretical effect involves the enormous tension carried by the string. Although the string itself is extremely thin, its tension could be immense. If a long straight cosmic string passed through a large object like Earth, The deficit angle in spacetime might produce a sudden shift in the relative positions of different parts of the planet. In some simplified models, the ground on one side of the string could appear to move slightly relative to the ground on the other side. The shift would occur almost instantly as the string passed. Some early theoretical papers even speculated that if the tension of the string were extremely high, the effect might resemble a narrow cut through matter along the path of the string. However, later analysis suggests that for most realistic cosmic string parameters, the effect would likely be much smaller. Instead of dramatic geological damage, the main signatures might involve tiny changes in distances or brief gravitational lensing effects. Because of the string's microscopic thickness, it would pass through atoms and molecules without interacting with them in the usual sense. Atoms would not collide with the string like they would with a solid object. The string would simply carry its geometric distortion through the material. Another interesting possibility involves gravitational waves. If a cosmic string loop oscillated near Earth, the gravitational waves produced by that motion could pass through our region of space. These waves would stretch and compress space-time slightly as they travelled. Modern detectors are already designed to measure such tiny distortions. However, the chances of a cosmic string loop passing close enough to produce a strong signal are extremely small. From a practical standpoint, the probability of a cosmic string intersecting Earth is considered extraordinarily low. Even if cosmic strings exist, they are likely spread across enormous volumes of space with vast distances separating them. The observable universe contains billions of galaxies, and Earth occupies a tiny fraction of that cosmic landscape. Encountering a cosmic string would therefore be extremely unlikely. Still, the idea provides an interesting way to think about how these objects interact with matter and space-time. Unlike most astronomical hazards, a cosmic string would not behave like a projectile or explosion. Its influence would come from the geometry of space-time rather than from physical contact. It would not crash into Earth. It would pass through quietly, altering the structure of space along its path. From our everyday perspective, such an event would be almost surreal. The sky might briefly display double stars. Distances between objects could shift slightly for an instant. Instruments measuring gravitational effects might record unusual signals. Then, just as quickly as it appeared, the phenomenon would vanish as the string continued its journey across the universe. While this scenario remains purely speculative, it highlights how unusual cosmic strings truly are. They challenge our intuition about what objects can be and how they interact with the world around them. Even when imagined passing through our own planet, their behaviour would not resemble anything we normally associate with physical objects. If these strange structures are possible consequences of the early universe's phase transitions, are cosmic strings the only kind of defect that could have formed during those dramatic moments in cosmic history? For most ideas in physics, there comes a moment when theory must confront observation. Mathematical equations can predict fascinating possibilities, but eventually scientists must ask a simple question. Does the universe actually contain the things those equations describe? Cosmic strings sit precisely at that crossroads. For decades they have occupied a curious position in cosmology. The mathematics that describe symmetry breaking and topological defects suggest that line-like structures could naturally form during the early phase transitions of the universe. The concept emerges from well-understood principles in field theory, and similar defects appear in many physical systems studied in laboratories. At the same time, no telescope has yet photographed a cosmic string, and no detector has produced a signal that everyone agrees can only be explained by one. Because of this, cosmic strings remain hypothetical. That does not mean scientists treat them as mere speculation. Instead, researchers approach the question carefully, combining theoretical predictions with increasingly precise observations of the universe. The search for cosmic strings is a good example of how modern cosmology works. Physicists begin with fundamental laws describing fields and particles. They examine what those laws predict under extreme conditions, such as the extraordinary temperatures present shortly after the Big Bang. From those predictions, they determine what observable signatures might appear billions of years later. Then astronomers look for those signatures in real data. If the predicted signals appear, the theory gains support. If they do not, the theory must be revised or constrained. Cosmic strings have gone through this process for many years. One of the earliest periods of excitement about them occurred during the 1980s and early 1990s. At that time, some cosmologists proposed that cosmic strings might have played a major role in forming galaxies. The idea was appealing. If strings stretched across the early universe, their gravitational effects could attract matter toward them. Dense regions would form along the strings, eventually collapsing into galaxies and clusters. This model suggested that the large-scale structure of the universe might resemble a network shaped partly by cosmic strings. For a while, this seemed plausible because the observed distribution of galaxies shows long filaments and walls separated by large voids. However, as measurements of the cosmic microwave background improved, scientists realized that the fluctuations in the early universe had a specific pattern consistent with a different explanation. That explanation involves inflation, a period of extremely rapid expansion that occurred very early in cosmic history. Inflation predicts that quantum fluctuations were stretched to enormous scales, creating the density variations that later grew into galaxies. The detailed structure of the cosmic microwave background matches the predictions of inflation remarkably well. These observations show that cosmic strings cannot be the primary cause of galaxy formation. Even though that particular role for cosmic strings was ruled out, the objects themselves were not eliminated. Instead, the observations place limits on how strong the strings could be. If cosmic strings exist, their tension must be small enough that they do not produce fluctuations larger than those seen in the cosmic microwave background. These limits help narrow the range of theoretical possibilities. Another area where researchers search for evidence involves gravitational lensing. As discussed earlier, a cosmic string passing between Earth and a distant galaxy could create two nearly identical images of that galaxy. Unlike ordinary gravitational lenses, which distort and magnify images, a cosmic string lens would produce almost perfect duplicates separated by a narrow gap. Astronomers have scanned large regions of the sky looking for such pairs. Occasionally they find galaxies that appear very similar to one another, raising the possibility that they might be lensed images of the same object. But when scientists analyze the spectra and detailed structures of these galaxies, they usually discover that the similarities are coincidental. So far, no confirmed cosmic string lens has been identified. Another promising approach involves gravitational waves. Cosmic string loops, if they exist, would oscillate and emit gravitational radiation. Over time, the combined signals from many loops could produce a background of gravitational waves detectable by sensitive instruments. Recent years have seen remarkable progress in gravitational wave astronomy. Observatories such as LIGO and Virgo have detected signals from merging black holes and neutron stars, confirming that spacetime ripples can be measured directly. In addition, networks of radio telescopes monitoring pulsars have begun detecting evidence of a low-frequency gravitational wave background. Scientists are currently studying these signals carefully. The most likely explanation involves pairs of supermassive black holes orbiting each other in distant galaxies. However, researchers are also investigating whether cosmic strings might contribute to the signal. If the background contains certain characteristic features, it could hint at the presence of oscillating string loops across the universe. Another line of evidence comes from the cosmic microwave background itself. High-resolution maps of the microwave sky allow cosmologists to search for unusual patterns that might indicate the presence of cosmic strings in the early universe. As described earlier, moving strings could produce narrow temperature discontinuities, known as the Kaiser-Stebbins effect. Detailed studies of data from the Planck satellite and other experiments have looked for such features. While no clear detection has been made, the data place increasingly strict limits on the possible tension and abundance of cosmic strings. Each new experiment narrows the range of parameters where strings could exist. Even though this might sound discouraging, it actually represents progress. Science often advances by eliminating possibilities until the remaining explanations become clearer. Another intriguing possibility involves extremely light cosmic strings predicted by certain modern theories. These strings would carry less tension than the original grand unified model suggested. Because they are lighter, their gravitational effects would be weaker and harder to detect. At the same time, they might still produce detectable gravitational waves or other subtle signals. Some of these ideas connect cosmic strings with concepts from string theory. In certain versions of string theory, objects known as cosmic superstrings could form during the early universe. These objects share some properties with traditional cosmic strings, but may interact differently when they intersect. For example, cosmic superstrings might reconnect less frequently than ordinary cosmic strings. This difference could lead to distinct patterns in the gravitational waves they produce. If future observations detect gravitational waves with the right characteristics, scientists may be able to distinguish between different types of strings. The question of whether cosmic strings really exist, therefore, remains open. Theoretical arguments suggest that they are possible. Observations have not yet confirmed them, but neither have they completely ruled them out. This situation is common in cosmology. Many phenomena predicted by theory take decades to confirm because the signals are subtle and require extremely sensitive instruments to detect. Gravitational waves themselves were predicted for nearly a century before technology became advanced enough to measure them directly. Cosmic strings may require a similar level of patience. New observatories planned for the coming decades will expand our ability to observe the universe in ways that were impossible before. More powerful telescopes will map billions of galaxies with extraordinary precision. Next generation gravitational wave detectors will listen to spacetime across a wide range of frequencies. Improved measurements of the cosmic microwave background will reveal even smaller fluctuations in the early universe. Each of these tools increases the chances that cosmic strings, if they exist, might eventually be detected. If such a discovery occurs, it would have profound implications. It would confirm that the early universe experienced phase transitions that produced topological defects in its fundamental fields. It would reveal new information about the energy scales involved in those transitions. Perhaps most importantly, it would provide direct evidence about physics operating at energies far beyond what current particle accelerators can reach. Even without a confirmed detection, the search itself continues to teach scientists more about the universe. By testing theories against observations, researchers refine their understanding of how the cosmos evolved from its earliest moments to the vast structure we see today. Cosmic strings remain one of the more intriguing possibilities emerging from this effort. They might exist as faint relics from the universe's first fractions of a second, stretching across immense distances yet thinner than anything we can imagine. Or they might exist only in the equations describing how the early universe could have behaved. For now, the evidence remains uncertain, but the universe still holds many secrets, and each new generation of observations brings us closer to answering one of the most fascinating questions in modern cosmology. If these ancient threads truly formed during the earliest transitions of the cosmos, they might still be waiting somewhere out there, hidden within the vast fabric of space. Far beneath the familiar layers of matter and energy that make up the visible universe, physicists suspect that an even deeper level of reality may exist. At everyday scales, we see atoms, molecules, and planets. At smaller scales, we discover protons, neutrons, and electrons. Dig deeper still, and we encounter quarks, gluons, and the other particles described by the standard model of particle physics. Yet even this detailed picture may not represent the final layer of nature's structure. The standard model successfully explains a remarkable range of physical phenomena, from the behavior of subatomic particles to the forces that govern atomic interactions. However, it is widely believed to be incomplete. the model does not incorporate gravity in a consistent way, and it leaves unanswered questions about dark matter, dark energy, and the unification of forces at extremely high energies. Because of these gaps, physicists continue searching for deeper theories that could explain how the universe works at its most fundamental level. Cosmic strings appear naturally in several of these deeper theoretical frameworks. One of the most well-known attempts to move beyond the standard model is string theory. In this approach, the fundamental building blocks of nature are not point-like particles, but tiny vibrating strings. These strings are unimaginably small, perhaps around the Planck length, which is roughly 10 to the power of minus 35 meters. In string theory, different vibration patterns of these fundamental strings correspond to different particles. One vibration might behave like an electron, another like a photon, and others like particles that have not yet been observed. Although string theory remains highly speculative, it offers a mathematical framework that could potentially unify gravity with the other fundamental forces. Within this framework, objects similar to cosmic strings may arise in interesting ways. The strings described in string theory are microscopic and exist at scales far smaller than anything that could stretch across the universe. However, under certain conditions, larger structures known as cosmic superstrings might form during the early universe. These superstrings would be vastly larger than the tiny fundamental strings of the theory, extending across astronomical distances while still maintaining extremely small thickness. In some scenarios, cosmic superstrings could behave very much like the cosmic strings predicted by earlier field theories. They would carry enormous tension and energy along their length. They might move through space, reconnect with other strings, and form oscillating loops that emit gravitational waves. However, there could also be subtle differences. One of those differences involves the probability that two strings reconnect when they intersect. Traditional cosmic strings predicted by field theories are expected to reconnect almost every time they cross. Cosmic superstrings, on the other hand, might pass through each other without reconnecting in some cases. This difference could influence the overall structure of the string network in the universe. If reconnection happens less frequently, the network might contain more long strings and fewer loops. That would change the gravitational wave signals produced by the network, providing a potential observational clue. Another concept related to cosmic strings involves the idea of branes. In certain versions of string theory, our familiar universe might exist on a three-dimensional surface embedded within a higher dimensional space. These surfaces are called branes, short for membranes. According to this idea, particles and forces other than gravity may be confined to the brane we inhabit, while gravity can extend into additional spatial dimensions. During the early universe, interactions between branes could produce defects that resemble cosmic strings. For example, if two branes collided and then separated, they might leave behind one-dimensional structures stretched between them. These structures could appear in our universe as long, thin strings carrying enormous energy. Such possibilities illustrate how cosmic strings might connect cosmology with deeper layers of fundamental physics. Instead of being merely curious structures formed during symmetry-breaking transitions, they could be direct evidence of phenomena occurring at energy scales far beyond anything accessible in laboratories. The energy scales involved in grand unified theories are already far beyond the reach of particle accelerators. If cosmic strings or cosmic superstrings exist, they could provide clues about processes that occurred when the universe was less than a trillionth of a second old. That is an extraordinary thought. It means that the large-scale universe we observe today might contain relics from events that took place at energies billions of times greater than those produced in the most powerful experiments on Earth. Studying these relics could help scientists test ideas about how forces unify at extremely high energies. Cosmic strings also illustrate how simple mathematical concepts can lead to surprising physical consequences. Topological defects arise whenever a system undergoes a symmetry-breaking transition and different regions settle into different configurations. Similar defects appear in condensed matter systems such as liquid crystals, superconductors, and superfluids. In those systems, defects can form lines or vortices that move and interact. The mathematics describing these defects resembles the mathematics used to describe cosmic strings. This connection between laboratory physics and cosmology is valuable because it allows scientists to test certain ideas in controlled experiments. Although laboratory defects are not cosmic strings, studying them can provide insight into how networks of defects behave over time. Another intriguing possibility involves the relationship between cosmic strings and dark matter. Dark matter makes up most of the matter in the universe, yet it does not emit or absorb light. Its presence is inferred through its gravitational influence on galaxies and galaxy clusters. Some theories suggest that cosmic strings could interact with dark matter in subtle ways. For instance, the gravitational fields around strings might attract dark matter particles, creating narrow regions of enhanced density along the strings. These effects would likely be extremely difficult to detect, but they highlight the potential connections between different components of the cosmos. Cosmic strings could also serve as probes of the early universe's temperature and energy conditions. Because their tension depends on the energy scale of the phase transition that produced them, measuring that tension would provide information about the physical processes occurring at that time. If future gravitational wave observations reveal signals consistent with cosmic string loops, scientists might be able to estimate the string tension, and therefore the energy scale of the transition. This would effectively allow us to study physics from the earliest fractions of a second after the Big Bang. Such information would complement data from particle accelerators, astrophysical observations, and theoretical models. It could help answer fundamental questions about how the universe evolved from its earlier state to the complex cosmic web of galaxies we see today. Despite the excitement surrounding these possibilities, it is important to remain cautious. Many theoretical ideas in high-energy physics remain untested, and not all of them will ultimately prove correct. String theory itself has not yet produced experimental evidence confirming its predictions. Cosmic superstrings, if they exist, remain hypothetical objects. Nevertheless, the study of these ideas pushes the boundaries of our understanding. By exploring how cosmic strings might arise from deeper physical theories, scientists gain insight into the connections between the very small and the very large. The behavior of fields at microscopic scales can influence structures stretching across billions of light years. The universe therefore acts as a natural laboratory for physics at energies far beyond our technological reach. If cosmic strings are ever detected, they could serve as bridges between cosmology and the deepest levels of theoretical physics. Their presence would suggest that the universe carries traces of processes governed by principles we're only beginning to understand, and while these threads might originate in physics far deeper than the Standard Model, they would still be woven into the vast cosmic structure surrounding us today. When we look up at the night sky, the universe often appears quiet and spacious. Stars shine like scattered points of light. Galaxies drift across enormous distances, and between them lie vast regions that seem almost empty. From our everyday perspective, the cosmos can feel like a collection of isolated objects floating in a dark and silent expanse. But the deeper we study the universe, the more that picture begins to change. Astronomers mapping the distribution of galaxies have discovered that matter in the universe is not arranged randomly. Instead, galaxies gather into clusters link together in long filaments, and these filaments form an enormous network stretching across the observable universe. Between them lie vast cosmic voids where comparatively little matter exists. This pattern is known as the cosmic web. The cosmic web emerged over billions of years as gravity slowly pulled matter into denser regions. Tiny fluctuations in density present shortly after the Big Bang gradually grew, eventually forming the immense structures we observe today. When cosmologists visualize this large-scale structure, the universe begins to resemble something woven or interconnected rather than scattered and empty. Cosmic strings, if they exist, add an intriguing new layer to that picture. They would not be part of the cosmic web in the same way galaxies and clusters are. Instead, they would be far older structures, formed during the earliest phase transitions of the universe, long before the first stars ignited. Their presence would suggest that the universe contains not only the structures created by gravity, but also relics from the fundamental fields that shaped its earliest moments. In that sense, the universe could be thought of as containing multiple layers of structure. The most familiar layer is the one we see directly through telescopes: stars, planets, galaxies, and clusters. Beneath that layer lies the cosmic web created by gravity acting over cosmic time. And beneath even that, there may exist deeper features formed by the physics of the early universe itself. Cosmic strings would belong to that deepest layer. They would not be made of matter like stars or planets. They would instead be defects in the configuration of fields that filled the universe shortly after the Big Bang. These defects could stretch across enormous distances while remaining thinner than any particle we can observe directly. Because of their extraordinary tension and energy, they could influence space-time in subtle ways, bending the paths of light and generating gravitational waves as they move. If such strings formed during early symmetry-breaking transitions, they might still exist today as ancient remnants woven through the vastness of space. The image of a woven tapestry becomes a useful way to think about this possibility. In a tapestry, many different threads combine to create a larger pattern. Some threads form visible shapes and colours. Others lie beneath the surface, supporting the structure even though they are not immediately noticeable. Similarly, the universe may contain structures at many different levels. The galaxies and clusters we observe are like the visible patterns on the surface of the fabric. The dark matter that shapes the cosmic web forms another layer, influencing the pattern even though it cannot be seen directly. Cosmic strings, if they exist, could represent yet another set of threads running through the fabric of space-time itself. These threads would not be woven by human hands, but by the laws of physics operating during the earliest fractions of a second after the universe began expanding. The notion that the cosmos might contain such ancient features can feel almost poetic, but it arises from careful theoretical reasoning. Whenever a system undergoes a symmetry-breaking transition, defects can form. This principle is not limited to cosmology. It appears in many areas of physics, including condensed matter systems studied in laboratories. For example, when certain materials cool and change phase, they can develop line-like defects or vortices where the order of the system cannot align perfectly. These defects behave in ways that resemble the predicted behavior of cosmic strings. By studying these laboratory systems, physicists gain insight into how networks of defects might evolve over time. The same mathematical ideas used to describe vortices in superfluids or defects in crystals also apply to cosmic strings forming in the early universe. This connection illustrates one of the most fascinating aspects of physics. Similar patterns can appear across vastly different scales. The same principles governing microscopic systems can also shape structures spanning billions of light years. Cosmic strings highlight this connection beautifully. They are predicted by theories describing fields and symmetries at extremely high energies, yet their possible effects extend across the largest scales in the universe. If cosmic strings exist, they would also remind us that the universe we observe today carries traces of events that happened very early in its history. The earliest moments after the Big Bang were incredibly energetic and dynamic. Forces that are separate today may once have been unified. Fields may have transitioned between different configurations as the universe cooled. Each of these transitions had the potential to leave behind lasting imprints. Cosmic strings would be among the most dramatic of those imprints. Their immense tension would cause them to oscillate, reconnect, and form loops that radiate gravitational waves. Over billions of years, these processes could produce faint signals travelling through space-time. Modern detectors are only beginning to reach the sensitivity needed to search for such signals. Gravitational wave observatories, large sky surveys, and detailed maps of the cosmic microwave background all contribute pieces to the puzzle. With each new observation, scientists learn more about what kinds of structures could exist in the universe, and what kinds must remain only theoretical. Whether cosmic strings are eventually discovered or not, the search itself expands our understanding of the cosmos. It encourages scientists to explore the connections between particle physics, cosmology, and gravitational phenomena. It also reminds us that the universe is far more complex than it first appears. What looks like empty space may contain fields and structures shaped by events that occurred billions of years ago. The cosmos may carry subtle patterns imprinted during its earliest transformations. In this sense, the universe truly resembles a vast tapestry. Some threads are bright and obvious, like the stars scattered across the sky. Others are invisible, but still essential, like the dark matter guiding the formation of galaxies. And perhaps, hidden among those threads, there may exist even older strands formed during the universe's first moments. If future observations reveal their presence, cosmic strings would become one of the most remarkable discoveries in modern science. They would show that the fabric of space-time itself still carries the marks of its earliest history. For now, the idea remains a possibility waiting to be tested. Astronomers continue scanning the sky. Physicists refine their theories, and detectors grow more sensitive with each passing year. Somewhere within the immense structure of the universe, the answer may already exist, quietly stretched across the cosmos like a thread woven into the deepest layers of reality.